Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring the profound forces beneath our feet. The ground we walk upon feels solid and unchanging, yet it is constantly moving, breathing, and transforming in ways we rarely notice. Beneath the surface lies a world of immense power, ancient rhythms, and geological wonders that have shaped our planet for billions of years. The Earth trembles and shifts. Mountains rise and fall, and continents drift across the globe like rafts on an endless ocean. All of this happens beneath us, mostly unseen, mostly unfelt, yet always present. If you enjoy these quiet explorations, I invite you to like and subscribe, or share a simple thought down in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the calm understanding of our living planet to carry you. Let's begin. The Earth beneath us is always moving. Every moment of every day, the ground beneath your feet is in motion. The Earth's crust, that thin shell we live upon, is not a single solid piece, but rather a collection of massive plates floating on a layer of hot, flowing rock. These tectonic plates drift slowly across the planet's surface, moving at speeds so gradual they're measured in centimeters per year, about as fast as your fingernails grow. Yet over millions of years, these tiny movements reshape entire continents, build mountain ranges, and create the deep trenches of the ocean floor. This constant motion is the heartbeat of our planet. It's been happening since the Earth's crust first cooled and solidified billions of years ago. The process is called plate tectonics, and it is the engine that drives earthquakes, volcanic eruptions, and the slow dance of continents across the globe. Right now, as you rest here, North America is drifting away from Europe. India continues pushing into Asia, raising the Himalayas ever higher. The Pacific Plate slides beneath Japan, and the African continent is slowly splitting apart along the Great Rift Valley. Most of this movement is imperceptible to us. We go about our lives unaware that the ground itself is traveling, carrying us along on a journey that began long before humans existed and will continue long after we're gone. It's a humbling thought that even the most solid thing we know, the Earth itself, is fluid and dynamic when viewed across the vast stretches of geological time. Earthquakes happen because tectonic plates interact at their boundaries. Where tectonic plates meet, the Earth becomes restless. These boundaries are the most geologically active places on the planet, where the slow dance of continents becomes visible in sudden, dramatic ways. There are three main types of plate boundaries, each creating different kinds of earthquakes and geological features. At divergent boundaries, plates pull apart, creating new crust as molten rock rises from below. At convergent boundaries, plates collide, with one often sliding beneath the other in a process called subduction. At transform boundaries, plates slide past each other horizontally, grinding and catching as they go. The friction between these massive slabs of rock is tremendous. As plates try to move past each other, they don't slide smoothly. Instead, they stick and lock together, held in place by the rough surfaces grinding against one another. But the forces driving plate motion don't stop. Pressure builds and builds, year after year, decade after decade, sometimes for centuries. The rocks deform, bending and straining under the accumulating stress, storing energy like a compressed spring. Eventually, the stress becomes too great. The rocks can no longer hold. In an instant, they snap and slip, releasing all that stored energy at once. This sudden release is an earthquake. The ground lurches as the plates finally move, sometimes by several meters in just seconds. Seismic waves radiate outward from the point of rupture, traveling through the Earth at speeds of several kilometers per second, carrying that released energy to the surface, where we feel it as shaking. This cycle of stress, accumulation, and sudden release has been happening for billions of years. It's the way the Earth relieves the tension created by plate motion. Without earthquakes, the plates couldn't move, and without plate motion, our planet would be a very different place. There would be no mountains, no deep ocean basins, perhaps no continents as we know them. In a strange way, earthquakes are necessary for the Earth to be the dynamic, living world it is. Most earthquakes occur along the Ring of Fire. If you were to map every earthquake that happens around the world, a clear pattern would emerge. The vast majority cluster around the edges of the Pacific Ocean, forming a horseshoe-shaped band that stretches from New Zealand up through the Philippines and Japan, across to Alaska and down the western coasts of North and South America. This zone is called the Ring of Fire, and it's the most seismically active region on Earth. The Ring of Fire exists because of the Pacific Plate and the many smaller plates that surround it. As the Pacific Plate moves, it collides with or slides beneath the plates carrying continents around its edges. These are primarily convergent and transform boundaries, the types that generate the most powerful earthquakes. About 90% of the world's earthquakes happen along the Ring of Fire, and it's also home to about 75% of the world's active volcanoes. Countries within the Ring of Fire, places like Japan, Indonesia, the Philippines, Chile, and the western United States, have learned to live with this geological restlessness. Their cultures have adapted over centuries to the reality that the ground may shake without warning. Buildings are designed to sway rather than crack. Emergency plans are practiced regularly. Entire societies have been shaped by the understanding that they live on active plate boundaries. But the Ring of Fire isn't the only earthquake zone. A belt of seismic activity also stretches from Indonesia through the Himalayas to the Mediterranean, following the boundaries where the Indo-Australian plate collides with Eurasia and Africa. The East African Rift, where the continent is slowly tearing apart, generates earthquakes as well. Even areas far from plate boundaries can experience earthquakes, though these are less frequent and generally less powerful. The Earth's crust floats on a layer called the asthenosphere. To understand earthquakes, we must journey downward through the layers of the Earth. The outermost layer, the crust, is remarkably thin compared to the planet's overall size. Beneath the oceans, it averages only about 7 kilometers thick. Under continents, it's thicker, perhaps 30 to 70 kilometers, but this is still just a fraction of the Earth's 6,000-kilometer radius. The crust is cold and rigid, made of solid rock that fractures when stressed. Below the crust lies the mantle, which makes up about 84% of Earth's volume. The uppermost part of the mantle is also cold and rigid, and together with the crust, it forms what geologists call the lithosphere. This is the layer broken into tectonic plates, but deeper in the mantle, about 100 kilometers down, something changes. The rock is still solid, but it's hot enough to become soft and pliable over long time scales. This layer is called the asthenosphere. The asthenosphere behaves almost like an extremely thick, slow-moving fluid. Over thousands of years, it flows and circulates, driven by heat from even deeper in the Earth. The rigid lithospheric plates above float on this flowing layer, like rafts on a very viscous sea. As the asthenosphere circulates, it drags the plates along, causing them to move across the Earth's surface. This is the fundamental mechanism behind plate tectonics. The relationship between the rigid lithosphere and the flowing asthenosphere is key to understanding why earthquakes happen at the surface, but originate from processes deep below. The energy for plate motion comes from heat in the Earth's interior. left over from the planet's formation and continuously generated by radioactive decay. This heat drives convection in the mantle. Hot rock rises, cool rock sinks, creating circulation patterns that can last for hundreds of millions of years. The plates are passive passengers on this conveyor belt, but at their edges, where they interact with each other, the forces become concentrated, leading to earthquakes. Seismic waves travel through the entire planet. When an earthquake occurs, it doesn't just shake the ground at the surface. It sends waves of energy traveling through the entire Earth. These seismic waves come in several types, each moving differently through rock and revealing different information about both the earthquake and the planet's interior. Understanding these waves is crucial to understanding earthquakes themselves. The first waves to arrive are called P waves, or primary waves. These are compression waves, similar to sound waves, that travel through rock by alternately compressing and expanding it. P waves can move through solid rock, liquid, and gas, and they're the fastest seismic waves, traveling at speeds of 5 to 8 kilometers per second in the crust. Because they arrive first, P waves often provide the first warning that a stronger shaking is coming. Following the P waves are S waves, or secondary waves. These are shear waves that move rock side to side, perpendicular to their direction of travel. S waves can only move through solid material. They cannot travel through liquids. They're slower than P waves, typically moving at about 60% of the P wave speed. The time delay between the arrival of P waves and S waves at a seismometer tells scientists how far away the earthquake occurred. But the shaking doesn't stop with P and S waves. When these body waves reach the Earth's surface, they can convert into surface waves, which travel along the planet's outer layer rather than through its interior. Surface waves are slower than body waves, but often cause the most damage because they produce larger ground motions. There are two main types: love waves, which shake the ground horizontally, and Rayleigh waves, which create a rolling motion similar to ocean waves. These seismic waves don't just reveal information about earthquakes. They're also the primary tool scientists use to understand Earth's internal structure. By studying how seismic waves speed up, slow down, bend, and reflect as they pass through different materials, geologists have mapped out the planet's layers: the crust, mantle, outer core, and inner core. Earthquakes, in their destructive power, have paradoxically given us our clearest window into the hidden depths of our world. The magnitude scale measures energy release. When news reports describe an earthquake, they almost always mention its magnitude. This number, often given on the Richter scale, or the more modern moment magnitude scale, represents the amount of energy released by the earthquake. But what does this number really mean? And how do scientists calculate it? Magnitude is a logarithmic scale, which means each whole number increase represents a tenfold increase in the amplitude of seismic waves and about 32 times more energy release. An earthquake of magnitude 5 releases about as much energy as the atomic bomb dropped on Hiroshima. A magnitude 6 earthquake releases 32 times more energy, equivalent to about 32 Hiroshima bombs. A magnitude 7 releases 32 times more than that, and so on. The scale was originally developed by Charles Richter in the 1930s, using seismographs in California to study local earthquakes. His scale worked well for those conditions, but it had limitations when applied to larger or more distant earthquakes. Modern seismologists use the moment magnitude scale, which measures the total energy released by calculating the area of the fault that ruptured, how much it slipped, and the strength of the rocks involved. This scale works consistently across all earthquake sizes and distances. Earthquakes below magnitude 3 are generally not felt by people, though sensitive instruments can detect them. Magnitude 4 earthquakes might rattle dishes and cause light fixtures to swing. Magnitude 5 can cause minor damage to poorly constructed buildings. At magnitude 6, the shaking becomes strong enough to cause moderate damage in populated areas. Magnitude 7 earthquakes are major events that can cause serious damage over large regions. Magnitude 8 and above are great earthquakes, capable of devastating entire countries. The most powerful earthquake ever recorded was the 1960 Chile earthquake, with a magnitude of 9.5. It ruptured a fault segment over 1,000 kilometers long and caused tsunamis that crossed the Pacific Ocean, causing destruction as far away as Japan and the Philippines. The energy it released was equivalent to about 25,000 nuclear weapons. Such events, thankfully, are rare, occurring somewhere on Earth perhaps once per century. Earthquakes can last seconds or minutes, depending on their size. The shaking from an earthquake doesn't last long, but the duration depends on the earthquake's magnitude and your distance from its source. Small earthquakes, magnitude 3 or 4, typically last only a few seconds. The fault rupture happens quickly, releasing energy in a brief pulse, and the seismic waves pass by in moments. You might feel a sharp jolt or a quick rumble, then it's over. Larger earthquakes last longer because more of the fault ruptures. A magnitude 6 earthquake might shake for 15 to 20 seconds. A magnitude 7 could last 30 seconds to a minute. The massive 9.1 Tohoku earthquake in Japan in 2011 lasted between 3 and 6 minutes, depending on location. For those experiencing it, it must have felt endless, the ground rolling and shaking without respite, each second stretching out as the mind struggles to process the unnatural motion. This longer duration isn't just a matter of perception. During a great earthquake, the fault doesn't rupture all at once. Instead, the rupture propagates along the fault like a zipper opening, traveling at about 3 kilometers per second. If the fault is hundreds of kilometers long, the rupture takes time to complete. Meanwhile, waves from different parts of the rupture arrive at different times, and they can interact, sometimes reinforcing each other to create even stronger shaking. The duration of shaking affects both people and structures. Brief earthquakes may startle you, but allow little time for damage to accumulate. But when shaking continues for a minute or more, the repeated stress can cause cumulative damage to buildings. Weaker structures may survive the first few seconds, only to collapse later as the shaking continues. The psychological impact is profound as well. A few seconds of shaking is frightening, but manageable. Several minutes tests human endurance and can leave lasting emotional scars. Aftershocks follow nearly every major earthquake. The ground doesn't settle immediately after a major earthquake. In the hours, days, and weeks that follow, the affected region experiences a series of smaller earthquakes called aftershocks. These occur as the crust adjusts to the new stress distribution created by the main shock. Some aftershocks happen almost immediately, within seconds or minutes. Others come hours or days later. The largest aftershocks can be substantial earthquakes in their own right, sometimes causing additional damage to structures already weakened by the main event. The frequency and magnitude of aftershocks follow a predictable pattern described by Omori's law, formulated by Japanese seismologist Fusakichi Omori in 1894. The number of aftershocks decreases roughly with the inverse of time since the main shock. Many aftershocks happen in the first hours and days, then they taper off gradually. However, aftershocks can continue for months or even years after a great earthquake, though they become increasingly rare as time passes. The largest aftershock is typically about 1 magnitude unit smaller than the main shock, though this is just a statistical tendency, not a strict rule. After a magnitude 7 earthquake, The largest aftershock might be magnitude 6, still a significant earthquake. In rare cases, what initially seems like the main shock is actually a foreshock, followed by an even larger earthquake. This happened in Japan in 2016, when a magnitude 6.2 earthquake was followed 2 days later by a magnitude 7.0 event. Living through an aftershock sequence can be psychologically exhausting. Just as people begin to recover from the trauma of the main earthquake, another jolt sends them diving for cover again. The uncertainty of when the next aftershock will hit, and how strong it might be, creates ongoing stress. Yet aftershocks are a natural part of the earthquake cycle, the Earth's way of redistributing stress and reaching a new equilibrium after the sudden displacement of the main shock. Foreshocks sometimes warn of larger earthquakes to come. Before some major earthquakes, the affected region experiences a series of smaller earthquakes called foreshocks. These are similar to aftershocks, but happen before the main event rather than after it. Foreshocks occur for the same reason. Stress is building on the fault, and smaller portions of it slip before the main rupture occurs. Unfortunately, foreshocks are only identifiable as such in hindsight. At the time they occur, there's no reliable way to distinguish a foreshock from any other small earthquake. About half of major earthquakes are preceded by foreshocks, but the other half strike without this warning. The foreshocks themselves can begin anywhere from seconds to weeks before the main shock, making them an unreliable predictor. A small earthquake might be followed by a larger one in a few hours, or it might be an isolated event that's not followed by anything significant. This uncertainty makes earthquake prediction extraordinarily difficult. Scientists have studied foreshock sequences extensively, looking for patterns that might provide warning of an impending major earthquake. Some foreshocks show a distinctive signature in their seismic waves, or occur in a particular spatial pattern, but these clues are subtle and not always present. Even when they are detected, there's often not enough time to issue meaningful warnings or evacuate populations. The most famous foreshock sequence occurred before the 2009 L'Aquila earthquake in Italy. A swarm of small earthquakes had been shaking the region for months, causing anxiety among residents. Some local officials attempted to reassure the public that a major earthquake was unlikely, while others warned that the situation was dangerous. When a magnitude 6.3 earthquake struck, killing over 300 people, the incident sparked controversy about the responsibility of scientists to communicate earthquake risk to the public. Earthquake prediction remains one of science's greatest challenges. Despite decades of research and technological advances, scientists cannot predict when or where the next major earthquake will strike. They can identify areas at high risk based on fault locations and historical patterns. They can calculate probabilities, saying that a particular region has, for example, a 30% chance of experiencing a major earthquake in the next 30 years, but pinpointing a specific date, time, and location remains beyond our current capabilities. The fundamental problem is that earthquake generation is a complex process involving many variables. The strength and distribution of stress on a fault, the properties of the rocks, the presence of fluids, temperature, and countless other factors all influence when and how a fault will rupture. Small changes in any of these variables can have large effects, making the system sensitive to initial conditions in a way that's difficult to model or predict. Many phenomena have been proposed as earthquake precursors: unusual animal behavior, changes in groundwater levels, electromagnetic anomalies, release of radon gas, even strange cloud formations. While some of these phenomena do occasionally occur before earthquakes, they also occur at other times when no earthquake follows. None has proven reliable enough to serve as a prediction method. For every apparent success, there are many false alarms or earthquakes that strike without any precursor. Some countries, particularly China, have made concerted efforts to develop earthquake prediction capabilities. There have been a few apparent successes, most notably the prediction of the 1975 Haicheng earthquake, which led to an evacuation that may have saved many lives. However, this success was followed by failures, including the devastating 1976 Tangshan earthquake, which struck without warning. The scientific consensus today is that short-term earthquake prediction, meaning prediction with enough precision to warrant evacuation, is not currently possible. Early warning systems provide precious seconds of warning. While prediction remains elusive, early warning is achievable. Earthquake early warning systems detect the initial P waves from an earthquake, which travel faster than the more destructive S waves and surface waves. By detecting these first arrivals near the earthquake's epicenter, the system can send alerts to areas farther away, providing seconds to tens of seconds of warning before strong shaking arrives. These precious seconds may not sound like much, but they can save lives. Automated systems can shut down trains to prevent derailments, close gas valves to prevent fires, and stop elevators at the nearest floor. Surgeons can step back from delicate procedures. Factory workers can shut down dangerous machinery. People can drop, cover, and hold on before the shaking starts. In some cases, early warning systems have successfully prevented disasters that would have been much worse without that brief advance notice. Japan has one of the most sophisticated earthquake early warning systems in the world, refined through decades of experience with seismic hazards. During the 2011 Tohoku earthquake, the system provided warnings up to 80 seconds before the strongest shaking reached Tokyo, about 370 kilometers from the epicenter. These warnings were broadcast on television, radio, and mobile phones, giving millions of people time to prepare. The United States is developing its own system called Shake Alert, covering the West Coast. Mexico City has operated an early warning system since the 1990s, using sensors along the coast to detect earthquakes before their waves reach the city. These systems represent a pragmatic approach to the earthquake hazard. Since we cannot predict earthquakes, we focus instead on detecting them the moment they start and alerting people in harm's way as quickly as possible. It's not perfect, but it works. The focus is where the earthquake starts, deep underground. Every earthquake has a point of origin, the exact spot where the fault first begins to rupture. This point is called the focus, or hypocenter, and it's located somewhere along the fault plane, usually several kilometers below the Earth's surface. The depth of the focus is an important characteristic of an earthquake, influencing how strongly it's felt at the surface and what kind of damage it might cause. Shallow focus earthquakes, with focuses less than 70 kilometers deep, are generally the most dangerous. The seismic waves have less distance to travel through the Earth before reaching the surface, so they lose less energy along the way. This means stronger shaking at the surface and greater potential for damage. Most of the world's damaging earthquakes are shallow focus events, including many along the San Andreas Fault in California and the North Anatolian Fault in Turkey. Intermediate focus earthquakes occur between 70 and 300 kilometers deep. These are less common and often associated with subduction zones, where one plate dives beneath another. The deeper focus means surface shaking is generally less intense, though the effects can still be felt over a very wide area. Deep focus earthquakes, below 300 kilometers, are even rarer and usually cause little damage despite potentially large magnitudes, simply because the energy has so far to travel. The deepest earthquakes occur around 700 kilometers below the surface, in the transition zone of the mantle. Below this depth, The pressure is so great that rocks can no longer fracture the way they do near the surface. Instead of brittle failure, the rocks deform plastically, flowing rather than breaking. This effectively sets a lower limit on how deep earthquakes can occur. The existence of deep focus earthquakes was once puzzling to scientists, as the normal mechanism of friction on faults shouldn't work at those depths and pressures. The current explanation involves phase changes in minerals, where the crystal structure suddenly shifts, releasing energy in the process. The epicenter is the point on the surface directly above the focus. While the focus is where the earthquake actually happens, the epicenter is the point on Earth's surface directly above the focus. It's the epicenter that usually appears on maps and in news reports, representing the geographic location of the earthquake. The distance from the epicenter determines, in part, how strongly the earthquake is felt at different locations, though local soil conditions and geological structure also play important roles. Determining the epicenter is one of the first tasks after an earthquake occurs. Seismologists use data from multiple seismic stations, measuring the time difference between the arrival of P waves and S waves at each station. Because these waves travel at different speeds, the time difference indicates how far away the earthquake was from that particular station. By combining data from at least 3 stations, scientists can triangulate the epicenter's location. In the past, this process took hours or even days. Today, automated systems can calculate preliminary epicenter locations within minutes, sometimes seconds, of an earthquake. This rapid determination is crucial for emergency response, helping authorities understand which communities are likely to be affected and where to send aid. The initial location estimate may be refined as more data becomes available, but even a rough location is valuable for coordinating relief efforts. The epicenter is also important for understanding earthquake hazards. Maps of historical seismicity show where epicenters have clustered in the past, revealing active faults and earthquake-prone regions. These patterns help scientists assess earthquake risk and guide building codes and land use planning. Areas near known epicenters of past major earthquakes are likely to experience similar events in the future, though the timing remains unpredictable. Intensity describes how strongly shaking is felt. While magnitude measures the energy an earthquake releases, intensity describes how that shaking is experienced at different locations. The same earthquake will have different intensities in different places, depending on distance from the epicenter, local geology, building construction, and other factors. A magnitude 7 earthquake might cause violent shaking near its epicenter, but be barely felt 200 kilometers away. The modified Mercalli intensity scale is the most commonly used system for measuring intensity in the United States. It ranges from I, not felt at all, to 12, total destruction. The scale is based on observable effects. Does the shaking wake people from sleep? Do pictures fall from walls? Are buildings damaged? Do landslides occur? Unlike magnitude, which is determined by instruments, intensity is assessed through reports from people and surveys of damage. In the lowest intensities, only sensitive instruments detect the earthquake. At intensity IV, objects rattle and hanging fixtures swing. At intensity VI, everyone feels the earthquake. Some people run outdoors and plaster cracks. At intensity VI, chimneys fall, frame buildings are damaged, and drivers have difficulty steering. At intensity X, most buildings are destroyed, bridges collapse, and railroad tracks bend. At the highest levels, waves are seen on the ground surface, and objects are thrown into the air. The intensity an earthquake produces at any location depends on many factors beyond just magnitude and distance. Soft sediments amplify shaking more than solid bedrock. so buildings on fill or river valleys often experience more intense shaking than those on rock. The frequency content of the seismic waves matters too. Some buildings resonate at certain frequencies, amplifying the motion. The quality of construction makes an enormous difference. Well-built structures can withstand intense shaking that would destroy poorly constructed ones. Liquefaction turns solid ground into quicksand. One of the most dramatic earthquake hazards is liquefaction, a process that can turn apparently solid ground into something resembling quicksand. It occurs in loose, water-saturated sediments, typically sand or silt. When seismic waves pass through these sediments, the shaking causes the soil particles to compact. The water between the particles suddenly bears the weight of everything above it, and the soil loses its strength, behaving temporarily like a liquid. Buildings and other structures sitting on liquefied soil can sink, tilt, or even topple over, despite suffering no direct damage from the shaking itself. Roads buckle and crack, underground utilities break, retaining walls collapse. The effects can be devastating and are often among the most costly consequences of earthquakes. In some cases, sand and water are forced upward, erupting at the surface in sand blows or sand volcanoes, leaving evidence of liquefaction that geologists can study to understand ancient earthquakes. The 1964 Alaska earthquake demonstrated liquefaction's destructive power. In Anchorage, entire neighborhoods slumped and slid as the ground beneath them liquefied. The Turnagain Heights landslide destroyed 75 homes as a layer of liquefied clay allowed overlying material to slide toward the coast. In Niigata, Japan, during a 1964 earthquake, apartment buildings famously tilted over onto their sides, remaining largely intact but toppled by liquefaction. Predicting where liquefaction will occur requires understanding both the earthquake hazard and local soil conditions. Areas with loose young sediments near the water table are most susceptible. Coastal areas, river valleys, and reclaimed land are particularly vulnerable. Modern building codes in earthquake-prone regions often require soil investigations to identify liquefaction potential. In high-risk areas, ground improvement techniques like densifying the soil or installing deep foundations can reduce the hazard, though these measures add to construction costs. Tsunamis are ocean waves generated by undersea earthquakes. When a large earthquake occurs beneath the ocean, it can displace enormous volumes of water, generating waves that travel across entire ocean basins. These are tsunamis, a word from Japanese meaning harbor wave. Unlike wind-driven waves, which affect only the surface, tsunamis involve the entire water column from surface to seafloor. In deep water, they travel at speeds approaching a jet aircraft, up to 800 kilometers per hour, but with wave heights of only a meter or less, making them nearly undetectable to ships. As a tsunami approaches shallow coastal waters, its behavior changes dramatically. The wave slows down but grows much taller as water piles up. The height can increase by 10 times or more. The wave may appear as a rapidly rising tide rather than a breaking wall of water, though the effect is the same. Water floods inland, sometimes kilometers from the shore, carrying debris and destroying everything in its path. The water then retreats, pulling debris and sometimes people back out to sea. Multiple waves typically arrive, sometimes hours apart, and later, waves can be larger than the first. Not all undersea earthquakes generate tsunamis. The earthquake must be large, typically magnitude 7 or greater, and it must involve vertical movement of the seafloor. Thrust faults, where one section of crust moves up over another, are most effective at generating tsunamis. Strike-slip faults, where the motion is horizontal, generally do not produce significant tsunamis. The depth matters too. The shallower the earthquake, the more efficiently it couples with the overlying water. The most devastating tsunami in recorded history followed the 2004 Sumatra-Andaman earthquake, a magnitude 9.1 event. The tsunami it generated killed more than 230,000 people in 14 countries around the Indian Ocean. Waves reached heights of 30 meters in some locations. The event prompted a complete rethinking of tsunami hazard in the Indian Ocean region, which had no warning system at the time. Today, an extensive network of sensors and sirens provides warnings, though gaps remain in the system. Tsunami warning systems save lives. Following the devastating 1946 Aleutian Islands tsunami, which killed people in Alaska and Hawaii, the United States established the Pacific Tsunami Warning Center. Over the decades, the system expanded to include sensors throughout the Pacific Ocean and warning protocols for all at-risk countries. Today, similar systems exist for the Indian Ocean, the Caribbean, and the Mediterranean, though coverage and effectiveness vary. The warning system relies on two types of data. Seismic stations detect earthquakes and quickly calculate their magnitude, location, and depth. If an earthquake is large enough and occurs in a location that could generate a tsunami, warnings are issued to coastal areas. However, seismic data alone cannot confirm whether a tsunami actually formed or predict its size. That requires direct measurements from the ocean. Deep ocean tsunami detectors, called dart buoys, provide this confirmation. These systems consist of a seafloor sensor that measures pressure changes as tsunami waves pass overhead, connected to a surface buoy that transmits the data via satellite. Because tsunamis in deep water have small amplitudes, the sensors must be extremely sensitive. The system can detect a wave just 1 centimeter high, passing over the sensor in water thousands of meters deep. When a tsunami warning is issued, coastal communities have minutes to hours to evacuate, depending on their distance from the earthquake. Areas near the earthquake may have only minutes, sometimes too little time for official warnings to reach everyone. This is why education is crucial. People in coastal areas need to know that if they feel strong earthquake shaking, they should immediately move to high ground without waiting for official warnings. This simple knowledge has saved countless lives. Landslides and avalanches are triggered by earthquake shaking. The ground shaking during an earthquake can destabilize slopes, triggering landslides that are sometimes more destructive than the earthquake itself. Hillsides that appear stable under normal conditions can fail when seismic waves pass through, especially if the rocks or soil are already weak, weathered, or saturated with water. In mountainous terrain, earthquakes can trigger thousands of individual landslides, blocking roads, damming rivers, and burying communities. The 1970 Peru earthquake, magnitude 7.9, triggered an avalanche that became one of the deadliest individual disasters in South American history. A section of ice and rock broke away from the north peak of Huascaran, Peru's highest mountain. The debris roared down the valley at speeds exceeding 300 kilometers per hour, destroying the towns of Yungay and Ranrajirca and killing an estimated 22,000 people in a matter of minutes. In regions with deep soil or soft rock, earthquake-induced landslides can be widespread. The 2008 Wenchuan earthquake in China, magnitude 7.9, triggered about 200,000 landslides across an area of more than 35,000 square kilometers. These landslides caused about 1/3 of the total deaths from the earthquake. Some landslides dammed rivers, creating temporary lakes that posed ongoing hazards until the dams could be artificially drained or reinforced. Assessing landslide hazard requires understanding both earthquake shaking potential and slope stability. Steep slopes of weak rock or soil are most vulnerable, especially in wet conditions. Deforestation can increase landslide risk by removing vegetation that helps stabilize slopes. In many earthquake-prone regions, landslide hazard zones are mapped and considered in land use planning, though enforcement of restrictions varies. After major earthquakes, monitoring potentially unstable slopes is crucial, as they may fail during aftershocks or the next heavy rain. Fires often follow earthquakes in urban areas. Earthquake shaking can rupture gas lines, topple candles and heaters, damage electrical systems, and create countless sources of ignition. Meanwhile, broken water mains mean firefighters lack water to combat the resulting blazes. This combination has led to fires that caused more damage than the earthquakes themselves. The most infamous example is the 1906 San Francisco earthquake, where fire destroyed much of the city over 3 days, consuming about 25,000 buildings, while the fire department struggled with broken water mains and exhausted personnel. The 1923 Great Kanto earthquake that devastated Tokyo and Yokohama killed an estimated 105,000 people, with the majority of deaths caused by fires rather than building collapse. Firestorms swept through wooden neighborhoods, fueled by strong winds and fed by countless ignition sources. In Yokohama, fires destroyed 90% of the buildings. The fires burned for 2 days before burning out for lack of fuel. The disaster led to major changes in Japanese urban planning and construction. Modern cities face different but still serious fire risks following earthquakes. While wooden construction is less common in developed countries, earthquakes can still rupture gas lines and damage electrical systems. High-rise buildings contain complex electrical and mechanical systems that may be damaged by shaking. Chemical plants and refineries can suffer equipment failures that lead to fires or explosions. The 1994 Northridge earthquake in California caused numerous natural gas fires and damaged a major oil pipeline, creating fires that burned for days. Preventing post-earthquake fires requires multiple approaches. Automatic gas shutoff valves can stop the flow when shaking is detected. Buildings can be designed with seismically resistant electrical and gas systems. Water systems can include redundancy and interconnections to maintain firefighting capability, even if some pipes break. Fire departments in earthquake-prone areas train for scenarios where they must combat multiple fires with limited water. These preparations, combined with public education about shutting off utilities after earthquakes, help reduce the fire hazard. Building design makes the difference between life and death. The same earthquake produces vastly different outcomes, depending on building quality. A magnitude 7 earthquake in California might kill a handful of people, while a similar event in a developing country could kill tens of thousands. The primary difference is not the earthquake itself, but how buildings respond to shaking. Engineered structures designed to resist earthquakes can survive shaking that would reduce poorly constructed buildings to rubble. The fundamental challenge is that buildings are designed to support static loads, the weight of the structure itself and its contents. Earthquake forces are dynamic, pushing buildings sideways with accelerations that can exceed the force of gravity. Buildings must be both strong enough to resist these forces and flexible enough to absorb energy without collapsing. Achieving this balance requires careful engineering and quality construction. Modern earthquake-resistant design incorporates several principles. Symmetric building forms perform better than irregular ones. Strong connections between components prevent the building from coming apart during shaking. Reinforcing steel within concrete provides both strength and ductility. Shear walls and braced frames resist lateral forces. Base isolation systems, which place bearings between the building and its foundation, allow the ground to move while the building remains relatively still. But good design is only part of the solution. construction quality matters enormously. If reinforcing steel is inadequately tied together, if concrete is poorly mixed, if connections are weak, the building will not perform as designed. Corruption and cost-cutting have led to catastrophic failures in numerous earthquakes. The 2008 Wenchuan earthquake in China collapsed many schools, while surrounding buildings survived, raising questions about construction quality. The 2009 L'Aquila earthquake in Italy killed students when their dormitory collapsed. Later investigations revealed it was not built to code. Unreinforced masonry buildings are particularly vulnerable. Before modern building codes, many structures were built of unreinforced masonry, brick or stone walls held together only by mortar. These buildings are beautiful and have stood for centuries, but they are highly vulnerable to earthquake shaking. The walls are heavy and brittle, lacking the tensile strength to hold together when shaken. Without reinforcement, brick walls can crack, bulge outward, and collapse, especially at corners and around openings, like windows and doors. Unreinforced masonry buildings remain common in many earthquake-prone regions. In the United States, cities like San Francisco, Los Angeles, and Seattle contain thousands of such structures, many built before earthquake hazards were well understood. Their ornate facades add character to neighborhoods, but they are potential death traps in a major earthquake. The bricks can fall onto sidewalks below, killing pedestrians. Entire walls can collapse outward. Floors can pancake down as walls fail to support them. Retrofitting these buildings is technically feasible but expensive. Common approaches include adding reinforcement to walls, strengthening connections between walls and floors, and bracing parapet walls that extend above the roofline. Some jurisdictions have passed ordinances requiring owners to retrofit unreinforced masonry buildings, though implementation is often slow due to the costs involved. Balancing historic preservation with seismic safety remains an ongoing challenge. The deadliest earthquake in recent history, the 2010 Haiti earthquake, derived much of its catastrophic toll from masonry construction. The magnitude 7.0 earthquake struck near Port-au-Prince, where most buildings were concrete block or unreinforced masonry. An estimated 300,000 people died, and over 1 million were left homeless. While the earthquake was significant, the death toll reflected not just natural hazard, but also poverty, inadequate construction, and weak building code enforcement. Soft-story buildings can collapse in earthquakes. A soft-story building is one where a lower floor has large openings and less strength than floors above. Common examples include apartment buildings with parking garages on the ground floor, retail buildings with large storefront windows, or residential buildings with open first floors. These open spaces make the first floor much more flexible than upper floors, creating a weak point in the structure. During earthquake shaking, the soft story tends to deform much more than stiffer floors above. In a severe earthquake, all the deformation concentrates in the soft story, causing it to collapse, while upper floors remain relatively intact. The result is often a pancake collapse, where upper floors drop down onto the collapsed first floor, crushing anyone inside. This failure mode is particularly deadly because people have no warning and no time to escape. The 1989 Loma Prieta earthquake near San Francisco demonstrated the hazard of soft-story buildings. In the Marina District, numerous apartment buildings with garages on the ground floor suffered soft-story failures. Similar collapses occurred in the 1994 Northridge earthquake, where 16 people died in the collapse of one apartment building with a soft first floor. These disasters prompted retrofitting requirements for such buildings in California. Retrofitting a soft-story building involves strengthening the weak floor to be as strong as floors above. This might mean adding steel frames, installing shear walls, or placing steel plates over existing walls. The work is disruptive and expensive, often requiring tenants to relocate temporarily. Many building owners have resisted retrofitting requirements, and political battles continue over who should pay for improvements. Yet the alternative is clear. Without retrofitting, these buildings are likely to collapse in the next major earthquake, potentially killing dozens of people in each collapse. Base isolation allows buildings to ride out earthquakes. One of the most innovative approaches to earthquake-resistant design is base isolation, a technique that partially decouples a building from ground motion. The building sits on special bearings that allow it to move independently of its foundation. When the ground shakes, the bearings shift and deform, absorbing energy, while the building above remains relatively still. It's similar to how a person can balance on a moving bus by shifting their stance. The most common base isolation system uses laminated rubber bearings, which consist of layers of rubber alternating with steel plates. The rubber is flexible enough to accommodate large horizontal movements, while the steel plates prevent the bearings from bulging vertically. During an earthquake, these bearings can shift by 0.5 meter or more, allowing the ground to move while the building stays relatively motionless. Additional damping devices may be included to absorb energy and prevent excessive movement. Base isolation has been successfully implemented in buildings around the world. In the United States, San Francisco City Hall was retrofitted with base isolators in the 1990s. Los Angeles International Airport's Terminal 1 is base isolated. Numerous hospitals, museums, and data centers use the technology to protect critical functions or valuable contents. In New Zealand, Parliament buildings and Te Papa Museum in Wellington are base isolated, protecting both people and cultural treasures. The technology works best for buildings on firm ground and is less suitable for tall or flexible structures. Base isolated buildings typically experience about 1/4 the acceleration of similar fixed base buildings during earthquakes, greatly reducing damage and protecting contents. The main drawbacks are cost, which can add 10 to 15% to construction expenses, and the need for regular maintenance of the bearings. Despite these challenges, base isolation is increasingly seen as one of the most reliable earthquake protection strategies available. Damping systems absorb earthquake energy. Another approach to protecting buildings is to install damping systems that absorb earthquake energy. These systems work like shock absorbers in a car, converting the kinetic energy of motion into heat. By dissipating energy, dampers reduce the amount of shaking the building experiences and the forces that structural elements must resist. Several types of dampers are used, each with advantages for different applications. Viscous dampers contain a thick fluid that resists being pushed through small openings. As the building sways, pistons move through the fluid, dissipating energy. These dampers are effective across a wide range of frequencies and are used in numerous buildings worldwide. Friction dampers work by sliding metal plates against each other, with the friction converting motion into heat. Tuned mass dampers use a large mass, often concrete or steel, mounted on bearings at the top of a building. Springs and dampers connect the mass to the building, and it's tuned to vibrate at the building's natural frequency, counteracting the building's motion. The Taipei 101 skyscraper in Taiwan contains one of the world's largest tuned mass dampers, a steel sphere weighing 730 metric tons, suspended from the tower's top. During typhoons and earthquakes, the sphere swings in opposition to the building's movement, reducing acceleration at the top by about 40%. It's visible to visitors, who can watch it move on windy days. The system not only protects against earthquakes, but also improves comfort during regular wind events. Damping systems can be particularly effective when retrofitting existing buildings. Adding dampers is often less invasive than major structural modifications. Fluid viscous dampers were added to San Francisco's Golden Gate Bridge to protect against earthquakes. The bridge's main cables support thousands of tons suspended over water, making seismic protection crucial. Dampers at the bridge towers allow the deck to move during earthquakes, while preventing excessive forces in the cables and towers. Some animals may sense earthquakes before humans do. Throughout history, people have reported unusual animal behavior before earthquakes. Dogs barking frantically, horses refusing to enter barns, birds flying erratically, even snakes emerging from hibernation in winter. These reports span cultures and centuries, suggesting something beyond mere superstition. The question is whether animals truly sense something humans cannot, and if so, what they're detecting, and whether it could provide useful warnings. Several mechanisms have been proposed. Animals might feel the initial P waves, which arrive before more destructive S waves and surface waves. With different sensory capabilities, some animals might be more sensitive to these subtle vibrations than humans. Another hypothesis involves changes in the Earth's magnetic field before earthquakes, which some animals might detect. Birds, fish, and some mammals use Earth's magnetic field for navigation and might be disrupted by anomalies. Changes in groundwater chemistry, release of gases, or shifts in static electricity are other possibilities. Scientific evidence remains mixed. Some laboratory studies have shown behavioral changes in animals before earthquakes, but controlled experiments are difficult because earthquakes are unpredictable. In China, where earthquake prediction efforts have been more aggressive, officials have sometimes used reports of animal behavior as one factor in issuing warnings. The partial success predicting the 1975 Haicheng earthquake included reports of unusual animal behavior, though how much weight this carried in the decision to evacuate is debated. The challenge is that animals behave unusually for many reasons unrelated to earthquakes. Without a clear understanding of what they're sensing, how reliably, and how far in advance, animal behavior cannot serve as a practical warning system. Still, the observations are intriguing and remind us that earthquake prediction involves detecting subtle changes in the Earth, changes that might affect living creatures in ways we don't fully understand yet. Continued research may eventually reveal whether folklore holds scientific truth. Seismometers detect ground motion, too small to feel. The instruments that detect earthquakes, called seismometers or seismographs, are marvels of sensitivity. Modern seismometers can detect ground movements smaller than the diameter of an atom. They record vibrations from earthquakes on the other side of the planet, register the rumble of distant storms, even pick up the minute compression of the Earth's crust from atmospheric pressure changes. This extraordinary sensitivity allows seismologists to detect and locate earthquakes that no human would ever feel. The basic principle behind a seismometer is simple. A mass suspended in a frame remains stationary due to inertia, while the ground moves beneath it. In early instruments, a pen attached to the mass drew traces on rotating paper drums, producing the classic squiggly lines that symbolize earthquakes. Modern seismometers use electronics to measure the relative motion between the mass and the frame, converting it to digital data that can be analyzed by computers. Seismic networks consist of many seismometers spread across a region or around the world. Each station continuously records ground motion and sends data to central processing centers. When an earthquake occurs, computers automatically analyze the incoming signals, calculate the location and magnitude, and disseminate information within minutes. The global seismic network is so comprehensive that earthquakes of magnitude 5 or larger can be detected and located anywhere on Earth. These instruments do more than just detect earthquakes. They're used to monitor volcanoes, as magma movement generates small earthquakes. They help verify compliance with nuclear test ban treaties by detecting underground nuclear explosions. They contribute to fundamental research on Earth's internal structure. The seismometer, first invented in the late 19th century, remains one of geology's most important tools, quietly listening to the planet's every tremor. Earthquakes happen on every continent. While most earthquakes concentrate along plate boundaries, no region of the world is completely safe. Even areas far from active faults experience earthquakes occasionally. These intraplate earthquakes, as they're called, are less frequent than those at plate boundaries, but they can be just as destructive when they occur. The central and eastern United States, for example, experiences significant earthquakes, despite being far from the Pacific margin. The most powerful earthquakes in the contiguous United States occurred not in California, but in Missouri. The New Madrid earthquakes of 1811 to 1812 were a series of events estimated at magnitude 7 to 8. They rang church bells in Boston, over 1,000 miles away, and temporarily reversed the flow of the Mississippi River. The region remains seismically active, though at lower levels, and geologists worry that a repeat of the early 19th century events would devastate the now heavily populated central Mississippi Valley. Australia, often thought of as geologically stable, experiences an earthquake large enough to cause damage somewhere on the continent, about once every 5 years. Most are small and occur in unpopulated areas, but occasionally they strike near cities. Earthquakes have been recorded in every Australian state and territory. The continent's interior contains ancient faults that occasionally reactivate under the stresses transmitted through the Indo-Australian plate. Even the stable interiors of continents carry ancient scars, faults from long-ago tectonic events. These faults can slip when the right combination of stress and weakness occurs, generating earthquakes. Because such events are rare, buildings in these regions often aren't designed to resist earthquakes, making them vulnerable when seismic activity does occur. Raising awareness of earthquake hazards in regions that rarely experience strong shaking remains an ongoing challenge for seismologists and emergency managers. Induced earthquakes result from human activities. Not all earthquakes are natural. Human activities can trigger earthquakes, a phenomenon called induced seismicity. The most common causes are fluid injection into the ground, reservoir impoundment behind dams, mining, and geothermal energy production. While induced earthquakes are typically smaller than major natural ones, they can still cause damage and concern, especially in areas not accustomed to seismic activity. Wastewater injection from oil and gas operations has caused a dramatic increase in earthquake activity in parts of the United States. Oklahoma, which averaged 1 or 2 magnitude 3 or larger earthquakes per year historically, experienced hundreds annually starting around 2010. The earthquakes result from injecting wastewater deep underground, where it increases pore pressure on faults, making them more likely to slip. Some of these earthquakes exceeded magnitude 5, causing damage to buildings and infrastructure. Large dams can also trigger earthquakes by impounding massive volumes of water. The weight of the water compresses the crust below, while water seeping into the rock increases pore pressure. Both effects can trigger slip on nearby faults. The most dramatic example was the 1967 Koyna earthquake in India, magnitude 6.3, which occurred near a large reservoir and killed about 200 people. Numerous other cases of reservoir-triggered seismicity have been documented worldwide. Mining, particularly when rock is removed and voids are created, can also induce earthquakes. Deep mines sometimes experience rock bursts, sudden violent failures of stressed rock. Geothermal energy projects, which inject water into hot rock to produce steam, have triggered small earthquake swarms in several locations. Understanding and managing induced seismicity is increasingly important as these activities expand. In some cases, operations can be modified to reduce earthquake risk, such as by limiting injection rates or volumes. The San Andreas fault is slowly tearing California apart. The San Andreas fault is perhaps the world's most famous earthquake fault, a 1,200-kilometer scar running through California from the Salton Sea to Cape Mendocino. It marks the boundary between the Pacific Plate and the North American Plate, two massive pieces of Earth's crust grinding past each other at about 5 centimeters per year. Over millions of years, this motion has displaced rocks by hundreds of kilometers, carrying pieces of Southern California northward. The fault is actually a fault system, a complex zone of breaks and fractures rather than a single clean line. In some places, the two sides slide past each other relatively smoothly in a continuous creep. In other sections, the fault is locked, accumulating stress that will eventually be released in a major earthquake. The southern section, from the Salton Sea to San Bernardino, hasn't ruptured in over 300 years and is considered overdue for a major earthquake. The big one, as Californians call it, refers to the anticipated magnitude 8 or larger earthquake on the San Andreas Fault. Geologic evidence shows such earthquakes occur on average every 150 to 200 years, though the intervals are irregular. The last major earthquake on the southern San Andreas was in 1704, meaning the region is within the window when the next could occur. When it does, it will cause catastrophic damage and billions of dollars in losses. Despite the threat, California continues to grow, with millions living near the fault. The state has invested heavily in earthquake preparedness, with strict building codes, early warning systems, and public education campaigns. Retrofitting older buildings continues, though many vulnerable structures remain. The question is not whether the big one will happen, but when, and how well prepared California will be when it does. The Cascadia subduction zone threatens the Pacific Northwest. While California's earthquake risk is well known, the Pacific Northwest faces a threat that was only recognized relatively recently. The Cascadia subduction zone, where the Juan de Fuca Plate dives beneath North America, extends from northern California to British Columbia. This fault is capable of producing magnitude 9 earthquakes and massive tsunamis, yet it has been quiet throughout recorded history in the region, creating a false sense of security. Geologic evidence reveals the fault's violent past. Layers of tsunami-deposited sand found in coastal wetlands, drowned forests of trees that died simultaneously, and written records from Japan of a mysterious tsunami in 1700, all point to a massive earthquake on January 26, 1700. The earthquake likely reached magnitude 9, with shaking lasting 4 to 5 minutes and a tsunami crossing the Pacific to devastate Japanese coastal villages. Research shows that Cascadia produces megathrust earthquakes on average every 300 to 600 years, though intervals vary widely. The last one was 320 years ago, meaning the fault could rupture at any time, though it might not happen for centuries. When it does, the shaking will be intense throughout the Pacific Northwest, and a tsunami will strike the coast within 15 to 30 minutes, leaving little time for evacuation. The region's population has grown enormously since the hazard was recognized in the 1980s. Seattle, Portland, and Vancouver are major cities built on or near the fault. Much of the existing infrastructure, including buildings, bridges, and lifelines like water and power systems, was built without consideration of this risk. A massive effort is underway to retrofit critical facilities and educate the public, but progress is slow. The Cascadia earthquake, when it comes, will be one of the worst natural disasters in North American history. Transform faults allow plates to slide past each other. While some plate boundaries involve plates colliding or pulling apart, others are characterized by horizontal motion, with plates sliding past each other like cars in adjacent lanes. These are transform faults, and they're capable of generating devastating earthquakes. The most famous transform fault is the San Andreas in California, but they exist throughout the world, both on land and beneath the oceans. Transform faults typically produce earthquakes shallower than those at subduction zones, meaning the shaking can be intense at the surface. The motion is primarily horizontal, though there's often some vertical component as well. Over time, transform motion creates distinctive landscapes with offset ridges, sag ponds, and linear valleys marking the fault trace. In California, driving along certain roads, you can see clear evidence of the lateral motion that has occurred over millions of years. Not all transform faults are as dangerous as the San Andreas. The length of the fault, how much of it can rupture in a single event, and the rate of motion all influence earthquake potential. The North Anatolian Fault in Turkey is another major transform fault that has produced numerous devastating earthquakes. It runs east-west across the country for about 1,500 kilometers, with the Anatolian Plate moving westward relative to the Eurasian Plate at about 2.5 centimeters per year. In the ocean, transform faults connect segments of mid-ocean ridges, where new crust is being created. These oceanic transform faults can be hundreds of kilometers long and are marked by deep troughs in the seafloor. They're seismically active, but pose little direct threat to humans since they're far from population centers. However, they're important for understanding plate tectonics and the forces that shape our planet's surface. Subduction zones produce the world's largest earthquakes. The most powerful earthquakes on Earth occur at subduction zones, where one tectonic plate dives beneath another, descending into the mantle. The interface between the two plates, called the megathrust fault, can rupture across hundreds of kilometers at once, releasing enormous amounts of energy. All earthquakes of magnitude 9 or greater in modern history have occurred at subduction zones, as have many of the most deadly earthquakes and tsunamis. Subduction zones encircle much of the Pacific Ocean, forming the most active portions of the Ring of Fire. Japan sits above the junction of 4 plates, with subduction occurring on its eastern side, where the Pacific Plate dives beneath it. South America's west coast marks, where the Nazca Plate subducts beneath the South American Plate, generating earthquakes in Chile, Peru, and Ecuador. The Aleutian Islands in Alaska are a volcanic arc created by subduction of the Pacific Plate beneath North America. The largest earthquake ever recorded, the 1960 Chile earthquake with magnitude 9.5, occurred at a subduction zone. It ruptured over 1,000 kilometers of the fault interface, and the shaking lasted about 10 minutes. The tsunami it generated killed people in Hawaii, Japan, and the Philippines. The second largest, the 1964 Alaska earthquake at magnitude 9.2, also occurred at a subduction zone, rupturing 800 kilometers of fault and causing massive ground displacement. Subduction zone earthquakes occur because the descending plate doesn't slide smoothly into the mantle. Instead, it sticks against the overriding plate, locked by friction. As the plates continue to converge, the overriding plate deforms, typically bending downward. Stress builds for decades or centuries until it exceeds the strength of the lock. When the fault ruptures, the overlying plate springs back upward, often displacing the seafloor by several meters and generating a tsunami. Normal faults form where the crust is pulling apart. In some regions, tectonic forces are pulling the Earth's crust apart rather than pushing it together or sliding it sideways. Where this occurs, the crust thins and breaks along normal faults, with blocks of crust dropping down relative to adjacent blocks. This process creates distinctive landscapes with alternating mountain ranges and valleys, like those seen in the Basin and Range province of the western United States. Normal fault earthquakes tend to be smaller than those on thrust faults because the orientation of stress makes it harder for normal faults to accumulate as much strain. However, they can still be destructive, especially in populated areas. The 2016 Amatrice earthquake in Italy, magnitude 6.2, occurred on a normal fault in the Apennine Mountains and killed nearly 300 people as centuries-old stone buildings collapsed. Greece is another region dominated by normal faulting. As the Aegean Sea spreads open, the country's numerous earthquakes, combined with its ancient architecture, create ongoing seismic risk. The East African Rift System, where the African continent is slowly splitting apart, is the world's most spectacular example of normal faulting. The rift creates a chain of deep valleys, lakes, and volcanoes, stretching from Mozambique to the Red Sea. Normal faulting is also how mid-ocean ridges spread, creating new sea floor. As plates pull apart at these underwater mountain ranges, magma rises from below to fill the gap, solidifying into new oceanic crust. The process occurs mostly beneath the oceans and is generally not felt on land, though Iceland, which sits atop the mid-Atlantic ridge, experiences earthquakes from this process. The island is literally being pulled apart, with its western half attached to North America and its eastern half to Europe. Reverse and thrust faults form where crust is compressed. Where tectonic plates collide, the crust is compressed, and rocks respond by breaking along reverse or thrust faults. These are faults where one block of crust moves up and over another, thickening the crust and building mountains. The geometry is opposite that of normal faults and reflects compressive rather than extensional stress. Thrust faults are simply low-angle reverse faults, with the distinction being somewhat arbitrary. The world's great mountain ranges were built primarily by thrust faulting. The Himalayas, still rising as India plows into Asia, contain numerous thrust faults that accommodate the collision. Large earthquakes along these faults are common and deadly. The 2015 Gorkha earthquake in Nepal, magnitude 7.8, killed nearly 9,000 people and damaged or destroyed nearly 900,000 structures. The earthquake occurred on a thrust fault beneath the Himalayas. Thrust faults can also exist at subduction zones, though the geometry there involves one plate sliding beneath another at the surface rather than stacking of crustal blocks. The megathrust faults at subduction zones are a special type of thrust fault, capable of the world's largest earthquakes. Their low angles and vast areas allow them to accumulate enormous strain and rupture across huge distances. In fold and thrust belts, like those found in the Zagros Mountains of Iran or the Canadian Rockies, thrust faulting creates distinctive patterns where rock layers are folded and broken, then stacked like shingles on a roof. These zones may have formed millions of years ago, but can remain seismically active. Ancient faults that seem dormant can suddenly reactivate if the stress field changes or if enough stress accumulates. This makes seismic hazard assessment challenging in such regions. Earthquake swarms consist of many events without a clear main shock. Not all earthquake sequences follow the pattern of main shock followed by aftershocks. Sometimes a region experiences an earthquake swarm, where many earthquakes of similar magnitude occur over days, weeks, or months, with no single event standing out as the main shock. Swarms can involve dozens, hundreds, or even thousands of individual earthquakes, creating ongoing anxiety for affected communities. Earthquake swarms often occur in volcanic regions or areas with geothermal activity. The movement of magma or fluids beneath the surface can trigger numerous small earthquakes as rock fractures in response to changing pressure. The Long Valley caldera in California has experienced multiple swarm sequences, sometimes with thousands of earthquakes in a few days. While these swarms can be alarming, they don't necessarily indicate an imminent volcanic eruption. Swarms also occur along some fault systems, where stress is accommodated through many small events rather than infrequent large ones. The Salton Sea region in Southern California regularly experiences swarms, sometimes involving thousands of earthquakes below magnitude 4. Scientists monitor these carefully, as a swarm in this region could potentially trigger a large earthquake on the southern San Andreas fault, though this has not yet occurred. The challenge with swarms is that they create uncertainty. Each earthquake in the sequence could potentially be a foreshock to something larger, or the entire sequence could gradually die out without a major event. Probabilistic forecasting helps quantify these chances, but communicating risk during an ongoing swarm is difficult. How do you advise people when the chance of a major earthquake is elevated, but still relatively low? Balancing public safety with avoiding unnecessary alarm remains an ongoing challenge. Slow slip events release stress gradually over days or weeks. While most earthquakes involve sudden, violent slip-on faults, some faults accommodate motion through slow slip events, also called silent earthquakes. During these events, the fault slips at rates thousands of times slower than regular earthquakes, taking days to months to complete. A slip that would occur in seconds during a magnitude 7 earthquake might take several weeks in a slow slip event, releasing the same amount of motion but without generating damaging seismic waves. Slow slip events were first discovered in the 1990s. Using GPS measurements, scientists noticed that monitoring stations would suddenly begin moving at accelerated rates, continuing for days or weeks before returning to normal. The pattern indicated fault slip, but seismometers detected little or no shaking. This revealed a completely new way that faults can move, one that had been invisible before precise space-based positioning became available. The Cascadia subduction zone experiences slow slip events every 14 to 15 months, lasting several weeks each time. During these events, the fault slips by a few centimeters, accommodating some of the motion between the Juan de Fuca and North American plates. Similar events occur at subduction zones in Japan, New Zealand, Mexico, and elsewhere. They're often accompanied by tremor, a weak but persistent seismic signal distinct from regular earthquakes. The relationship between slow slip and regular earthquakes is not fully understood. Some researchers think slow slip might trigger larger earthquakes by changing stress on nearby locked sections of faults. Others suggest slow slip could actually reduce earthquake hazard by releasing stress gradually. Monitoring these events provides valuable information about how faults behave and could potentially improve earthquake forecasting, though much remains to be learned about these mysterious silent earthquakes. Paleoseismology reveals ancient earthquakes. Earthquakes leave clues in the geological record that persist long after the shaking stops. Paleoseismology is the study of these prehistoric earthquakes through evidence preserved in sediments, rocks, and landforms. By trenching across faults and carefully examining the exposed layers, geologists can identify past earthquakes, estimate their magnitudes, and determine how often they occur. This information is crucial for assessing seismic hazards in regions where written records are short or non-existent. The technique involves digging trenches perpendicular to a fault and logging the exposed walls in meticulous detail. Each earthquake that ruptures the surface disrupts soil layers, creating distinctive patterns. Displaced layers, folded strata, and upward injection of liquefied sediment all indicate past earthquakes. By carefully analyzing these features and determining their sequence, Paleoseismologists reconstruct a timeline of earthquakes stretching back thousands of years. Dating these ancient earthquakes requires techniques like radiocarbon dating of organic material buried in the sediments. A piece of charcoal from a campfire might be found in a layer offset by a fault. By dating the charcoal, scientists can determine when the layer was deposited and establish a maximum age for the earthquake that displaced it. Combining dates from multiple horizons allows estimation of when each earthquake occurred, though with uncertainty that increases with age. Paleoseismology revealed the hidden threat of the Cascadia subduction zone. Before this work, the Pacific Northwest was thought relatively safe from major earthquakes. But studies of coastal marshes revealed repeated layers of sand deposited by tsunamis, submerged forests where trees died simultaneously, and other evidence pointing to great earthquakes every few centuries. This discovery transformed understanding of seismic hazards in the region and prompted major changes in building codes and emergency planning. GPS stations monitor tectonic plate motion in real time. Modern technology allows scientists to watch tectonic plates move in real time with millimeter precision. Networks of GPS stations continuously measure their positions relative to satellites orbiting Earth. Over months and years, these measurements reveal the steady motion of plates and the accumulation of strain on faults. This information helps assess earthquake hazards and improve understanding of tectonic processes. In California, hundreds of GPS stations track the motion of the Pacific Plate relative to North America. The data clearly show most of the boundary motion occurring on the San Andreas fault system, though some happens on parallel faults as well. Areas where GPS shows the plates are locked together, not slipping freely, are where stress accumulates and future earthquakes will occur. By mapping these locked patches, scientists identify the most hazardous sections of faults. GPS data also reveals transient events that might otherwise go unnoticed. The slow slip events discussed earlier were discovered through GPS measurements. When a slow slip event occurs, GPS stations in the area suddenly start moving faster than usual, then return to normal as the event ends. This would be invisible without precise positioning technology. GPS networks also detect the gradual ground deformation before some volcanic eruptions, providing warning time. After an earthquake, GPS stations record the permanent ground displacement caused by fault slip. This information helps seismologists understand exactly how the fault ruptured, which is difficult to determine from seismic waves alone. Following the 2011 Tohoku earthquake in Japan, GPS data showed some stations moved several meters horizontally and dropped by more than a meter vertically. This detailed picture of the earthquake's effects contributes to improved models of how megathrust faults behave. InSAR satellites can detect ground deformation from space. Another powerful technology for monitoring earthquakes and tectonic motion is InSAR, which stands for Interferometric Synthetic Aperture Radar. Satellites, equipped with radar instruments, repeatedly image the Earth's surface. And by comparing images taken at different times, scientists can detect ground deformation with centimeter to millimeter precision across wide areas. This has revolutionized earthquake science, allowing researchers to study earthquakes and faults in remote regions with no ground instruments. InSAR works by measuring how the distance between the satellite and ground changes over time. When the ground moves toward or away from the satellite, even slightly, the radar signals phase shifts. By comparing phases from different images, scientists create interferograms showing ground deformation as colorful fringes. Each fringe represents a specific amount of motion, allowing quantitative measurements. The technique can map ground deformation over entire earthquake rupture zones, revealing details impossible to obtain any other way. The 1999 Hector Mine earthquake in California was one of the first events where InSAR provided detailed images of surface deformation. The data showed the extent of fault rupture and how much slip occurred at different locations along the fault. More recently, InSAR revealed that the 2017 Pohang earthquake in South Korea, previously attributed to geothermal operations, had a more complex relationship between natural and induced processes than initially thought. InSAR is particularly valuable for studying earthquakes in inaccessible or politically sensitive regions. After earthquakes in Afghanistan, Tibet, or other remote areas, InSAR provides information that would be difficult or impossible to gather on the ground. The technique also detects slow ground deformation between earthquakes, revealing how faults behave during the decades-long intervals between major events. As satellite technology improves and more radar satellites are launched, InSAR's role in earthquake science continues to grow. Ancient civilizations recorded earthquakes in their writings. Long before modern instruments existed, people documented earthquakes through written accounts, inscriptions, and oral traditions. These historical records extend the earthquake catalog beyond the instrumental era, providing information about past events that helps assess long-term earthquake patterns. The oldest earthquake records come from China, where court officials documented celestial and terrestrial phenomena, including earthquakes, for more than 3,000 years. Chinese historical records describe earthquakes with remarkable detail, sometimes noting the date, location, duration of shaking, damage patterns, and unusual phenomena. The records mention landslides, ground cracks, changes in water levels in wells, and lights in the sky. While some descriptions are clearly embellished or mixed with supernatural interpretations, the core information about when and where earthquakes occurred is generally reliable and has been valuable for assessing seismic hazards. Mediterranean civilizations also recorded earthquakes. Greek and Roman writers described devastating earthquakes that destroyed cities and changed coastlines. The destruction of the ancient city of Helike in Greece in 373 BCE, swallowed by the sea during an earthquake and tsunami, was well documented and influenced Greek philosophy and literature. Archaeological evidence confirms many of these accounts, with excavations revealing collapsed buildings and destruction layers matching historical descriptions. In the Americas, indigenous peoples recorded earthquakes through oral traditions and, in some cases, pictographic records. Aztec codices contain references to earthquakes, using the symbol Olin, meaning movement or earthquake. Native American oral traditions along the Pacific Northwest coast describe the ground shaking and the sea retreating before a great wave arrived, likely referring to the 1700 Cascadia earthquake. These accounts, passed down through generations, were initially dismissed by scientists, but later recognized as describing a real event. The elastic rebound theory explains how earthquakes work. Understanding why earthquakes happen required a conceptual breakthrough that came after the devastating 1906 San Francisco earthquake. Studying the offset fences and roads along the San Andreas fault, geologist Harry Reid developed the elastic rebound theory, which remains the fundamental explanation for how earthquakes work. The theory describes earthquakes as the sudden release of elastic strain energy stored in deformed rocks. Reid observed that the land on opposite sides of the San Andreas fault had been gradually moving in opposite directions for years before the earthquake, based on surveys conducted before and after the event. This motion was accommodated not by continuous slip on the fault, which was locked, but by gradual bending and deformation of the crust near the fault. Like a stretched rubber band, the rocks stored elastic energy as they deformed. When the stress exceeded the friction holding the fault locked, the fault suddenly slipped, and the rocks snapped back toward their original shapes, releasing the stored energy as seismic waves. This theory revolutionized earthquake science because it explained the earthquake cycle: slow accumulation of strain through tectonic motion, followed by sudden release during an earthquake, followed by gradual strain accumulation again. It provided a physical mechanism for earthquakes, rooted in measurable tectonic processes. The theory predicts that earthquakes will recur on the same faults, though not necessarily at regular intervals, because the tectonic forces continuously operate. Elastic rebound theory also explains why aftershocks occur. The main shock doesn't relieve all the accumulated strain, and it creates new stress concentrations at the edges of the rupture zone. These areas readjust through aftershocks. The theory even explains foreshocks as small stress releases before the main rupture. More than a century after its formulation, elastic rebound remains central to earthquake science, though it has been refined and extended as understanding of fault mechanics has deepened. Stick-slip friction controls. When faults rupture, the behavior of faults between earthquakes is governed by friction, the resistance to sliding between two surfaces in contact. Most of the time, faults are stuck, held motionless by static friction despite the tectonic forces pushing on them. This is called the locked phase. As stress builds, the fault eventually reaches a critical point where static friction can no longer hold, and sliding begins. Once motion starts, kinetic friction takes over, which is typically lower than static friction, allowing rapid slip to occur. This is called the slip phase. This stick-slip behavior is familiar from everyday experience. When you push a heavy box across the floor, it resists until suddenly it breaks free and slides more easily. Faults behave similarly, but on a much grander scale. Laboratory experiments on rock samples show stick-slip behavior, with the samples periodically jerking as stress builds and releases. These lab earthquakes, though tiny, reproduce many features of real earthquakes, helping scientists understand the physical processes. The transition from stick to slip isn't instantaneous. A nucleation phase occurs where slip begins on a small portion of the fault and then either grows into a full earthquake or arrests. If the stressed area is large enough and conditions are right, the rupture propagates, growing into an earthquake. If not, the slip stays localized and might only be detectable as a micro-earthquake. Understanding nucleation is key to earthquake prediction, as it represents the critical moment when an earthquake begins. Unfortunately, detecting nucleation in progress remains extremely difficult. Not all faults exhibit perfect stick-slip behavior. Some faults creep continuously, accommodating motion without earthquakes. Others show mixed behavior, with some sections creeping and others locked. The Hayward Fault in California, which runs through the San Francisco Bay Area, exhibits significant creep in some locations. This creep is visible in offset curbs and buildings and can be measured precisely with instruments. However, other sections of the Hayward Fault are locked and capable of major earthquakes, making it one of the most hazardous faults in California. Fault roughness and geometry influence. Earthquake size. Faults are not smooth, planar surfaces, but rough, complex structures with bumps, bends, and branches, This roughness and geometric complexity strongly influences earthquake behavior. As a rupture propagates along a fault, it may encounter obstacles that slow or stop it. These barriers limit the size of earthquakes. Conversely, smooth sections of faults may allow ruptures to grow larger. A fault bend or step, where the fault trace changes direction or jumps to a parallel strand, often acts as a barrier to rupture propagation. Energy is required to break through these discontinuities, and if the available energy is insufficient, the rupture arrests. This is why earthquakes don't simply continue until they've broken every fault in a region. Natural barriers segment faults into patches that rupture individually in moderate earthquakes or together in great earthquakes when barriers are overcome. The roughness of fault surfaces at smaller scales affects the strength of faults and how they slip. Very rough surfaces have high friction and may accumulate more stress before slipping. Smooth surfaces, perhaps polished by previous earthquakes or coated with weak minerals like clay, may slip more easily. Some faults contain strong patches called asperities that resist slip and accumulate particularly high stress. These asperities may control when and where large earthquakes nucleate. Recent research suggests that fault roughness might follow fractal patterns, meaning the degree of roughness looks similar at different scales, from microscopic to kilometers. This self-similar structure could influence how earthquake ruptures propagate and why earthquake statistics follow particular patterns. Understanding fault geometry at all scales, from the microscopic roughness that determines friction to the large-scale bends that stop ruptures, is crucial for predicting earthquake behavior. Earthquake clusters can migrate along fault systems. Sometimes earthquakes don't occur randomly, but instead march progressively along a fault or between related faults over months or years. This phenomenon, called earthquake migration or clustering, suggests that stress changes from one earthquake influence where the next will occur. The pattern can be quite regular, almost like dominoes falling in sequence, though the mechanisms remain debated. One of the clearest examples occurred on the North Anatolian Fault in Turkey during the 20th century. Starting in 1939, a series of magnitude 7 earthquakes propagated westward along the fault, each earthquake occurring closer to Istanbul. The progression continued through 1999, with 11 major earthquakes over 60 years. Each earthquake appeared to increase stress on the adjacent fault segment to the west, bringing it closer to failure. This pattern raised concerns about the next segment near Istanbul, which remains unbroken and may be approaching rupture. Similar patterns have been observed on other faults. The East African Rift experienced a sequence of earthquakes, marching northward along the rift in the 1920s. In California, the San Andreas fault system has shown evidence of clustering, with active periods when multiple segments rupture within decades, separated by quieter centuries. These patterns are not perfectly regular or predictable, but they suggest that earthquakes are not independent events. Each changes the stress on nearby faults, influencing when and where future earthquakes occur. Stress transfer calculations help quantify these interactions. When a fault ruptures, it relieves stress where it slipped, but increases stress at the rupture's edges and on nearby faults. Areas of increased stress are more likely to experience future earthquakes, while areas of stress decrease may be temporarily safer. This concept has refined earthquake forecasting, allowing scientists to identify which faults are most likely to rupture next following a major earthquake. However, the calculations require detailed knowledge of fault geometry and rock properties, and uncertainties remain large. The Coulomb stress change concept explains earthquake triggering. To understand how one earthquake affects others, scientists calculate the Coulomb stress change, a measure combining the effects of shear stress that drives faulting and normal stress that resists it. When an earthquake occurs, it changes the stress field throughout the surrounding crust. Areas where Coulomb's stress increases become more likely to fail in future earthquakes, while areas where it decreases become temporarily more stable. The concept was named after French physicist Charles-Augustin de Coulomb, who studied friction in the 18th century. His work showed that the resistance to slip depends on both the frictional properties of surfaces and the normal stress pressing them together. Modern seismologists apply this principle to faults, calculating how earthquakes change both the shear stress, trying to make faults slip, and the normal stress, holding them together. Studies have shown that aftershocks preferentially occur in regions of positive Coulomb stress change. When maps of calculated stress changes are compared to where aftershocks actually occurred, the correlation is striking. Most aftershocks cluster in the lobes of increased stress surrounding the main shock rupture. This validates the physical basis of the calculations and demonstrates that stress changes really do influence future seismicity. The concept also explains how earthquakes can trigger others on different faults, sometimes faults oriented quite differently from the one that ruptured. The 1992 Landers earthquake in California was followed 3 hours later by the Big Bear earthquake on a different fault, 25 kilometers away. Calculations showed the Landers event increased stress on the Big Bear fault, likely bringing it to failure. Such dynamic interactions make earthquake sequences more complex than a simple main shock and aftershock pattern. Some faults produce characteristic earthquakes repeatedly. While each earthquake is unique, some faults appear to produce similar earthquakes repeatedly. The characteristic earthquake model suggests that for a given fault segment, the largest earthquakes rupture the same area, with similar magnitudes at somewhat regular intervals. The fault essentially has a preferred way of breaking, determined by its geometry, strength, and the stress applied to it. Evidence supporting this model comes from Paleoseismology and historical records. The Wasatch Fault in Utah shows evidence of repeated surface rupturing earthquakes on individual segments, each producing similar amounts of slip. In Japan, trenching across faults has revealed multiple prehistoric earthquakes with similar displacements. The San Andreas Fault at Parkfield, California, was thought to produce magnitude 6 earthquakes about every 22 years, leading to a prediction experiment that monitored the site intensively. However, the model has limitations. The Parkfield earthquake that was predicted for 1988 didn't occur until 2004, and even then, it showed important differences from previous events. While faults may favor certain rupture scenarios, they're not perfectly regular clocks. Variability in stress loading rates, strength along the fault, and interactions with other faults all introduce unpredictability. Some earthquakes break through barriers that stopped previous events, growing larger than characteristic size. The debate over characteristic earthquakes continues. Some seismologists think the model applies to certain faults under certain conditions. Others argue that earthquakes are inherently complex and rarely repeat exactly. The truth likely lies between these extremes. Faults probably have favored rupture patterns, but with enough variability that prediction based on recurrence intervals alone remains unreliable. Understanding both the patterns and the uncertainties is crucial for realistic hazard assessment. Seismic gaps may indicate where future earthquakes will strike. Along active faults, some sections rupture frequently, while others remain quiet for long periods. These quiet sections are called seismic gaps. The seismic gap hypothesis suggests that gaps represent locked fault segments where stress is accumulating and major earthquakes are overdue. Identifying gaps could therefore help predict where future large earthquakes will occur. making the concept attractive for hazard assessment. The idea gained prominence after successfully anticipating some earthquakes in the 1970s and 80s. Along subduction zones like those around the Pacific, maps showed some segments had recently ruptured, while others hadn't broken in a century or more. When major earthquakes subsequently filled some of these gaps, the hypothesis seemed validated. The 1985 Mexico earthquake, for example, occurred in a segment identified as a seismic gap. However, the hypothesis has significant limitations. Not all gaps fill with large earthquakes, and some areas that weren't identified as gaps produce major earthquakes. The 1995 Kobe earthquake in Japan occurred in a region not considered a high-priority gap. Some apparent gaps may actually be strong sections of faults that rarely break, rather than locked sections about to fail. Others may accumulate stress more slowly than expected, meaning they're not yet ready to rupture. Modern seismic hazard assessment still considers gaps, but within a broader, probabilistic framework. Rather than saying a gap will definitely produce an earthquake, scientists estimate the probability based on slip rates, time since the last earthquake, and other factors. This approach acknowledges both the logic behind the gap concept and the inherent uncertainties. Gaps remain one piece of information among many used to assess where future earthquakes are likely, but they're not a magic predictor. Earthquake. Early warning cannot predict earthquakes. It's important to understand what earthquake early warning can and cannot do. These systems do not predict earthquakes before they occur. They cannot tell you that an earthquake will strike tomorrow or next week. What they do is detect an earthquake the moment it starts and rapidly alert people who haven't yet felt the shaking. This distinction between prediction and early warning is crucial. Early warning works because seismic waves travel at finite speed. P waves, the fastest seismic waves, travel about 6 kilometers per second through the crust. The more damaging S waves and surface waves are slower. By detecting P waves near an earthquake's epicenter and rapidly calculating the earthquake's location and magnitude, the system can send alerts to areas farther away where strong shaking hasn't yet arrived. The warning time depends on distance from the epicenter. For someone directly above the focus, there is no warning time. Shaking arrives essentially instantly, but at 50 kilometers from the epicenter, there might be 10 seconds of warning. At 100 kilometers, perhaps 20 to 30 seconds. At 200 kilometers, a minute or more. This brief advance warning is enough for automated systems to take protective actions and for people to seek shelter under sturdy furniture or in doorways. The system's effectiveness depends on rapid detection and communication. Seismometers must detect the first P waves. Computers must calculate location and magnitude, and alerts must be transmitted, all within a few seconds. Modern systems accomplish this using simplified algorithms that sacrifice some accuracy for speed. The initial magnitude estimate might be off by half a unit, and the location might have some error, but getting useful information out quickly is more important than perfect precision. Users must understand these limitations and respond to warnings even though they sometimes will be false alarms or less severe than predicted. Drop, cover, and hold on is the safest action during shaking. When the ground begins to shake, your instinct might be to run outside, but this is actually one of the most dangerous things you can do. Falling objects, breaking glass, and collapsing walls make doorways and exits hazardous. The safest action is to drop to your hands and knees, take cover under a sturdy desk or table, and hold on until the shaking stops. This simple procedure, taught in earthquake drills worldwide, has saved countless lives. Dropping to the ground prevents the earthquake from knocking you down. Taking cover under a desk or table protects you from falling objects. which cause many earthquake injuries and deaths. Holding onto your shelter ensures you stay protected if it moves during shaking. If no table or desk is available, get against an interior wall, away from windows, and cover your head and neck with your arms. In bed, when an earthquake strikes, stay there and cover your head with a pillow, as getting up may expose you to more hazards. The myth of standing in a doorway comes from old adobe buildings, where door frames were the strongest part of the structure. In modern buildings, doorways are no safer than any other part of the room and leave you vulnerable to falling objects and moving doors. Another dangerous myth is the triangle of life concept, which advises lying next to large objects rather than under tables. This advice, based on anecdotal evidence from one rescuer, has been thoroughly debunked by engineers and emergency management professionals. After the shaking stops, hazards remain. Check for injuries and damage. If you smell gas or see broken electrical wires, evacuate if safe to do so. Be prepared for aftershocks, which can cause additional damage to weakened structures. If you're near a coast and felt strong shaking, move immediately to high ground in case of a tsunami. Having an emergency kit with water, food, first aid supplies, and a flashlight prepared before an earthquake makes the aftermath easier to manage. Practicing drop, cover, and hold on regularly helps the action become automatic, so you respond correctly, even when surprised and frightened. Earthquakes don't kill people, buildings do. This stark statement contains an important truth. The shaking itself, even in a magnitude 9 earthquake, doesn't directly kill people standing on firm ground outdoors. The danger comes from what humans have built. Buildings that collapse, walls that topple, heavy objects that fall, fires that spread through damaged structures. In regions with strong building codes and quality construction, the same earthquake magnitude that devastates one country might cause relatively few casualties in another. The 2010 Haiti earthquake, magnitude 7.0, killed an estimated 300,000 people in a country with a population of 10 million. Less than a year earlier, the 2009 L'Aquila earthquake in Italy, magnitude 6.3, killed about 300 people, despite similar intensity of shaking in the affected area. The difference was building quality. Haiti's informal construction, with little engineering input and poor concrete quality, collapsed readily. Italy's older buildings were vulnerable, but many met code standards and performed adequately. This disparity extends to economic impacts as well. The 2011 Christchurch earthquake in New Zealand, magnitude 6.3, caused about $15 billion in damage in a city of 400,000 people. Most modern buildings survived, but the economic disruption was enormous. Meanwhile, much larger earthquakes in remote areas with sparse population cause little damage simply because there's not much there to destroy. Earthquake risk is a combination of hazard and vulnerability. Reducing earthquake deaths requires improving buildings. This means both constructing new buildings to earthquake-resistant standards and retrofitting existing vulnerable structures. In developing countries, where most construction is informal and unregulated, providing access to simple earthquake-resistant designs and encouraging their use can dramatically reduce casualties. In developed countries with older building stock, identifying and retrofitting the most hazardous buildings prevents future tragedies. Earthquakes are inevitable, but earthquake disasters are not. With proper preparation, they become manageable events rather than catastrophes. Schools and hospitals require special earthquake protection. Some buildings are more critical than others. Schools and hospitals serve especially vulnerable populations and must continue functioning after earthquakes when they're needed most. A collapsed school kills children and devastates a community. A damaged hospital cannot treat earthquake casualties, multiplying the disaster's impact. Recognizing this, modern building codes typically impose stricter requirements on these essential facilities. Unfortunately, many schools and hospitals worldwide were built before earthquake-resistant design was understood or required. In China, the 2008 Wenchuan earthquake killed thousands of schoolchildren when poorly constructed schools collapsed. In Italy, university buildings have collapsed in recent earthquakes. In California, many older hospital buildings were vulnerable, leading to legislation requiring seismic retrofitting. The cost is substantial, but the alternative, hospitals out of service when most needed, is unacceptable. Protecting schools involves both structural and non-structural measures. The building must be designed to remain standing during strong shaking. But even if the structure survives, falling ceiling tiles, light fixtures, and bookshelves can kill or injure occupants. Securing non-structural elements is equally important. Hospitals face additional challenges because they contain heavy equipment, supplies that must not be contaminated, and patients who cannot easily evacuate. Operating rooms mid-surgery when an earthquake strikes must be able to safely complete procedures. Evaluating existing schools and hospitals for earthquake safety and prioritizing retrofitting where needed is an ongoing process in many earthquake-prone regions. The work is expensive and disruptive, sometimes requiring buildings to be closed during construction. However, the investment is worthwhile. Every child and patient deserves to be in a building that will protect them when the ground shakes. Ensuring this protection requires political will, adequate funding, and sustained effort, but it's achievable and essential. Cultural heritage sites face unique earthquake challenges. Ancient temples, historic city centers, and irreplaceable cultural monuments face special challenges during earthquakes. These structures were built centuries or millennia ago using traditional methods and materials. They often lack the steel reinforcement and engineered connections that make modern buildings earthquake-resistant, yet they're culturally priceless, and losing them would erase tangible connections to history. Protecting cultural heritage while respecting historical authenticity requires careful balance. Unreinforced stone or brick construction dominates historic buildings. Grand cathedrals, ancient Roman ruins, medieval castles, and traditional temples all share vulnerability to earthquake shaking. Heavy masonry walls and roofs create large inertial forces during earthquakes. Connections between walls and roofs are often weak. Decorative elements like towers, domes, and ornate facades are especially vulnerable. When these buildings collapse, they often do so catastrophically. Recent earthquakes have devastated cultural heritage. The 2015 Nepal earthquakes damaged or destroyed thousands of temples and monuments, including parts of the UNESCO World Heritage Sites in Kathmandu Valley. In Italy, earthquakes in 2009, 2012, and 2016 damaged countless historic churches and buildings in medieval hill towns. Each loss diminishes humanity's shared cultural wealth and impacts communities' identity and economy, as many depend on heritage tourism. Protecting heritage sites requires sensitive interventions. Engineers must improve seismic performance while preserving historical fabric and appearance. Techniques include adding hidden steel bracing, injecting grout into cracked masonry, installing base isolation under historic structures, and carefully reinforcing weak connections. International organizations like UNESCO work with local authorities on conservation that incorporates seismic protection. The goal is ensuring these irreplaceable structures survive for future generations while maintaining their authenticity and historic character. Bridges and elevated highways are particularly vulnerable. Bridges pose special earthquake challenges. They must span gaps while supporting heavy loads, often with limited support points. During earthquakes, different support points move differently, creating complex forces throughout the structure. Many older bridges were designed before earthquake forces were understood. Spectacular bridge collapses during earthquakes have prompted major changes in bridge design and retrofitting programs. The 1989 Loma Prieta earthquake in California caused the collapse of a section of the San Francisco-Oakland Bay Bridge and the collapse of the Cypress Street Viaduct, an elevated freeway section that pancaked, killing 42 people. The 1994 Northridge earthquake collapsed several freeway overpasses and damaged hundreds more. The 1995 Kobe earthquake in Japan dropped sections of elevated expressways. These disasters revealed vulnerabilities in bridge design and construction that were subsequently addressed. Common failure modes include columns shearing off due to inadequate reinforcement, spans falling off their supports, and soil liquefaction undermining foundations. Many older bridges have columns reinforced only with vertical steel bars and widely spaced horizontal hoops. During earthquake shaking, the concrete crushes and spalls away, leaving the vertical bars unsupported. They buckle, and the column fails, dropping the bridge deck. Modern designs include closely spaced spiral reinforcement that confines the concrete core and prevents this failure mode. Retrofitting bridges is expensive but necessary. California has spent billions reinforcing bridge columns, installing restraining devices to prevent spans from separating and improving foundations. Temporary closure of major bridges for retrofitting causes traffic nightmares but prevents potentially catastrophic failures. In earthquake-prone regions, designing bridges to survive major earthquakes is now standard, though many older structures still await upgrading. The cost of retrofitting is substantial, but losing critical transportation links after an earthquake would cripple emergency response and economic recovery. Dams must be especially resistant to earthquakes. Few earthquake scenarios are more frightening than a dam failure. Dams hold back enormous volumes of water, and their failure would release catastrophic floods downstream. Recognizing this, dam safety standards require that dams survive the maximum credible earthquake for their location, an event that might happen only once in thousands of years. The consequences of failure are so severe that designers err on the side of extreme conservatism. Different dam types respond differently to earthquakes. Earth dams, constructed from compacted soil and rock, are relatively flexible and can tolerate earthquake shaking if properly designed. However, they're vulnerable to liquefaction in their foundations or bodies. Concrete gravity dams, massive structures that resist water pressure through their weight, are rigid and can crack during intense shaking. Arch dams rely on transferring water pressure to rock canyon walls and are vulnerable if earthquake shaking damages the rock anchoring them. Several dams have failed or nearly failed during earthquakes. The Van Norman Dam in California came within inches of overtopping during the 1971 San Fernando earthquake. The lower San Fernando Dam's upstream slope failed, and thousands of people downstream were evacuated. The dam held, but the incident highlighted vulnerabilities in older earth dams. In China, hundreds of small dams failed during the 2008 Wenchuan earthquake, though fortunately, no catastrophic losses occurred because most were small reservoirs. Modern dam design includes seismic analysis and, for critical structures, instrumentation to monitor their condition during and after earthquakes. Following strong shaking, operators inspect dams for damage before allowing continued operation. Some high-hazard dams are being replaced or retrofitted to meet current standards. The potential consequences drive investment in seismic safety that might seem excessive for other structure types. When protecting lives of millions of people downstream, no level of safety is too high. Coastal communities face combined earthquake and tsunami threats. For communities along subduction zone coasts, earthquake hazards include both ground shaking and tsunamis. This double threat creates unique challenges. Building codes must address both requirements. Structures strong enough to survive earthquake shaking and elevated or inland enough to avoid tsunami inundation. Emergency plans must account for scenarios where earthquakes damage evacuation routes and warning systems before tsunamis arrive. Japan, with its long history of earthquakes and tsunamis, has developed sophisticated approaches. Coastal cities have seawalls designed to protect against tsunamis, though the 2011 Tohoku tsunami overwhelmed many. Evacuation routes are marked, and high ground or tall evacuation buildings provide refuge. Regular drills keep the population prepared. Warning systems provide minutes to tens of minutes of warning for distant tsunamis, though locally generated tsunamis may arrive too quickly for electronic warnings to help. In the Pacific Northwest, communities like Seaside, Oregon, face particularly severe challenges. The town sits on a low-lying peninsula, and when the Cascadia fault ruptures, residents will have perhaps 15 minutes to evacuate before tsunami waves arrive. The earthquake itself will damage roads and buildings, complicating evacuation. The community has designated tsunami assembly areas on high ground and built pedestrian bridges over highways to speed evacuation. Schools practice evacuations regularly, training even young children to respond quickly. Balancing normal life with hazard preparedness is challenging. Tsunami evacuation structures, with their elevated platforms and reinforced construction, are expensive. Building codes that prohibit development in inundation zones limit property rights and economic opportunities. Yet the alternative, doing nothing and accepting catastrophic losses when the inevitable event occurs, is unacceptable. Finding this balance requires community dialogue, scientific input, and political courage to implement protective measures, even when the threat seems distant. Tsunami warning systems require international cooperation. Tsunamis don't respect national boundaries. Generated by an earthquake in one country, they can cross entire ocean basins and devastate coastlines thousands of kilometers away. Effective warning systems require international cooperation to share seismic data, operate detection buoys in international waters, and coordinate warning dissemination. The Pacific Tsunami Warning System, established after the 1946 tsunami, is the world's oldest international tsunami warning system. The system includes seismic monitoring networks operated by member countries that share data in real time. When a potentially tsunami-genic earthquake occurs, analysts at warning centers in Hawaii, Japan, and Alaska evaluate the threat and issue warnings, watches, or advisories to member nations. Each country then decides how to respond, issuing local warnings, ordering evacuations, or taking other protective actions. The system has successfully warned of numerous tsunamis, allowing coastal communities to evacuate before waves arrived. The 2004 Indian Ocean tsunami revealed a critical gap. The Indian Ocean had no tsunami warning system, and no mechanism existed to alert the countries affected. Although seismologists worldwide recognized the earthquake's tsunamigenic potential within minutes, no coordinated system existed to warn at-risk coastlines. In the tsunami's aftermath, the international community established the Indian Ocean Tsunami Warning System, and similar systems were created for the Caribbean and Mediterranean. Challenges remain in ensuring warnings reach everyone who needs them. Warning centers can issue alerts, But getting those alerts to remote coastal villages, to fishermen at sea, and to tourists unfamiliar with local hazards remains difficult. Education is crucial. People must understand what warnings mean and how to respond. International exercises test the warning systems, but real events inevitably reveal gaps. Continuous improvement, sustained funding, and ongoing political commitment are necessary to maintain effective tsunami warning systems. Earthquake insurance helps communities recover. After major earthquakes, rebuilding can cost billions of dollars. Homeowners whose houses were destroyed, businesses whose buildings collapsed, and governments facing massive infrastructure repairs all need funding. Earthquake insurance provides financial protection, though coverage rates vary widely. In regions with high earthquake risk and mandatory coverage, like New Zealand, most property is insured. In other areas, including parts of California, most homeowners lack earthquake insurance. Earthquake insurance differs from standard property insurance because earthquake losses are spatially correlated. A single event can cause claims from thousands of policyholders simultaneously, creating enormous liability for insurers. To manage this risk, insurance companies use reinsurance, essentially insurance for insurers, and catastrophe bonds, securities that transfer risk to capital markets. These financial instruments allow the insurance industry to cover potential losses from major earthquakes. The cost of earthquake insurance reflects the risk. In high-hazard areas, premiums can be substantial, and deductibles often reach 10 to 20% of the insured value. Many homeowners decide they can't afford coverage or choose to self-insure, accepting the risk. After major earthquakes, governments often provide disaster assistance, but this typically covers only a fraction of losses. Uninsured property owners may face financial ruin if their largest asset is destroyed. Earthquake insurance programs vary internationally. New Zealand's Earthquake Commission provides basic coverage to all homeowners as part of standard fire insurance. Turkey requires earthquake insurance for formal buildings. California operates a state-backed earthquake insurance program, the California Earthquake Authority, created after insurers threatened to exit the market following the Northridge earthquake. Japan's system combines private insurers with government reinsurance. Each approach balances risk distribution, affordability, and the need to encourage mitigation measures while ensuring financial recovery capacity exists when disasters strike. Microzonation maps identify areas of higher and lower risk. Not all parts of a city face equal earthquake risk. Local geology, soil conditions, and topography dramatically affect ground shaking intensity. Microzonation is the process of mapping these variations within urban areas, identifying neighborhoods that will experience stronger or weaker shaking during earthquakes. These detailed maps guide land use planning, building codes, and emergency response planning. Areas underlain by soft soil or artificial fill generally experience stronger shaking than areas on bedrock. Soil amplification can double or triple the intensity of shaking. The 1985 Mexico City earthquake demonstrated this dramatically. The earthquake epicenter was 350 kilometers from Mexico City, yet certain neighborhoods built on the dried lakebed of Lake Texcoco experienced devastating shaking, while other parts of the city on volcanic rock were barely affected. Modern buildings in the lake zone collapsed, while colonial-era buildings on bedrock survived. Topography also matters. Ridgetops and cliff edges can experience amplified shaking due to focusing of seismic waves. Valley bottoms may see increased shaking as waves bounce off valley sides. Steep slopes are prone to landslides during earthquakes. All these factors are considered in microzonation studies. Geologists map surface geology, measure soil properties, and use theoretical and empirical models to predict shaking intensity. Microzonation maps inform building codes by allowing different requirements for different zones. Buildings in high amplification zones may need to be stronger or may be limited in height. Land use regulations can prohibit critical facilities like hospitals in particularly hazardous areas. Emergency planners use the maps to anticipate which neighborhoods will suffer worst damage. Some cities, like San Francisco and Tokyo, have very detailed microzonation maps developed through decades of study. Others, particularly in developing countries, lack this detailed knowledge, leaving residents unaware of localized hazards in their neighborhoods. Earthquake scenarios help communities prepare. Scenario planning involves developing detailed descriptions of hypothetical earthquake events and their consequences. These scenarios aren't predictions, but plausible future events used for planning purposes. By working through a scenario, emergency managers, government officials, and utilities can identify gaps in preparedness and develop coordinated response plans. Scenarios make the abstract earthquake threat concrete and actionable. The shakeout earthquake scenario, developed for Southern California, describes a magnitude 7.8 earthquake on the southern San Andreas fault. The scenario includes detailed maps of expected shaking, estimates of building damage, casualties, economic losses, and impacts on lifelines like water, power, and transportation. It describes conditions emergency responders would face: thousands of collapsed buildings, widespread fires, overwhelmed hospitals, and disrupted communications. Working through this scenario revealed many gaps in preparedness. The scenario became the basis for the Great Shakeout Earthquake Drill, where millions of people practiced drop, cover, and hold on simultaneously. Businesses, schools, and government agencies used the drill to test their emergency plans. Utilities practice coordinated restoration of services. Hospitals surge capacity plans. The scenario-based approach helped shift earthquake preparedness from abstract to practical, giving people and organizations specific situations to prepare for, rather than vague warnings about earthquake danger. Other regions have developed similar scenarios. Seattle has a magnitude 9 Cascadia scenario. San Francisco has a Hayward fault scenario. Tokyo has multiple scenarios for different possible earthquakes. These documents are typically public, allowing anyone to understand the potential impacts in their area. Beyond preparedness, scenarios inform policy decisions about building codes, retrofitting priorities, and infrastructure investments. By making future earthquake impacts tangible, scenarios motivate action that might otherwise be delayed when the threat seems distant or abstract. Community resilience determines recovery speed. Two communities struck by similar earthquakes may recover at vastly different rates. The difference often comes down to resilience, the ability to absorb a shock, adapt, and recover. Resilient communities have strong social networks, economic diversity, functioning governments, and populations with the resources and knowledge to rebuild. Less resilient communities may struggle for years or never fully recover. After the 2011 Christchurch earthquake in New Zealand, the city faced a long recovery. The central business district was severely damaged, and many historic buildings were demolished. Population declined as residents relocated to other cities. However, New Zealand's strong economy, effective government, and social safety net enabled gradual recovery. A decade later, much of the city has been rebuilt, though the character changed significantly. The recovery required sustained commitment and resources. In contrast, Port-au-Prince, Haiti remains partially in ruins more than a decade after the 2010 earthquake. Millions were displaced into temporary camps, and years later, many remained there. Weak governance, poverty, and limited resources hindered reconstruction. International aid helped, but couldn't substitute for strong local institutions and economic capacity. The earthquake exposed and exacerbated pre-existing vulnerabilities, and recovery has been incomplete. Building community resilience requires addressing social and economic factors beyond just physical infrastructure. Communities with high inequality, where many residents live in poverty, are less resilient because poor residents lack resources to rebuild. Communities that depend on a single industry may struggle if that industry is disrupted. Strong local government, community organizations, and social cohesion help communities organize recovery efforts and advocate for needed resources. Ultimately, reducing earthquake risk requires addressing broader social vulnerabilities, not just strengthening buildings. Traditional knowledge sometimes contains earthquake wisdom. Before modern science, communities living in earthquake-prone regions developed their own understanding of seismic hazards and protective measures. Some traditional building techniques incorporate earthquake-resistant principles discovered through trial and error over generations. This traditional knowledge is increasingly recognized as valuable, complementing scientific understanding and offering low-cost solutions appropriate for local contexts. In Peru, indigenous communities traditionally built with quincha, a technique using a wooden frame filled with woven cane and plastered with mud. The flexible frame can deform during earthquakes without collapsing, unlike rigid adobe walls. Japanese traditional temples use complex wooden joinery with no nails or bolts. The joints allow controlled movement and energy dissipation during earthquakes, protecting the structure. Some of these temples have survived hundreds of years and multiple major earthquakes. Traditional knowledge also includes site selection. In the Pacific Northwest, some Native American settlements were located on high ground, away from the coast. Oral traditions warned against building in certain areas, knowledge that makes sense in light of the Cascadia tsunami hazard recognized by modern science. In various cultures, stories of the sea withdrawing before great waves contain practical survival information encoded in myth and passed down through generations. However, not all traditional practices are effective, and romanticizing traditional knowledge while ignoring modern engineering would be a mistake. The key is integration, understanding what works in traditional approaches and combining it with scientific knowledge. In many developing regions, improved traditional techniques offer more realistic earthquake protection than expensive engineered construction. Respecting local knowledge while adding scientific understanding creates culturally appropriate solutions that communities are more likely to adopt and maintain. Children need special earthquake education and protection. Children are particularly vulnerable during earthquakes and require special consideration in preparedness efforts. They spend much of their time in schools, which must be safe structures. They may not understand earthquake hazards or know how to protect themselves. Traumatic earthquake experiences can have lasting psychological impacts on young children. Yet children also can be powerful agents for spreading earthquake preparedness information to families and communities. School-based earthquake education reaches children when they're most receptive to learning safety behaviors. Programs like the Great Shakeout teach drop, cover, and hold on through memorable drills. Children learn why earthquakes happen, what to do during shaking, and how to prepare emergency kits. Many programs give children assignments to develop family emergency plans, effectively using children to spread preparedness to households. Teachers report that children often take earthquakes more seriously than adults, asking to practice drills and ensuring family has supplies. Making schools physically safe is equally important. As discussed earlier, school buildings must be designed or retrofitted to survive earthquakes. Classrooms should have secured furniture and fixtures so they don't fall during shaking. Teachers need training on how to protect students during and after earthquakes, including plans for releasing children to parents when communications and transportation may be disrupted. Some schools in high-risk areas maintain emergency supplies to shelter students for days if necessary. The psychological impact of earthquakes on children can be long-lasting. Children who experience frightening earthquakes may develop anxiety, difficulty sleeping, or behavioral changes. They may worry about future earthquakes or resist going to school in damaged buildings. Child-focused counseling and maintaining normal routines, as much as possible, help children process their experiences and recover. Recognizing that children experience disasters differently than adults and providing appropriate support is crucial for community recovery. Earthquake early warning faces technical and social challenges. While earthquake early warning systems work in principle, implementing them effectively faces both technical and social challenges. The technical challenges include detecting earthquakes reliably, calculating magnitudes quickly, and disseminating alerts before damaging waves arrive. Social challenges include ensuring people understand and appropriately respond to warnings, addressing equity in warning access, and managing false alarms. Magnitude estimation is particularly challenging for large earthquakes. Standard algorithms may underestimate magnitude in the first seconds after rupture begins, when fast decisions are needed. A magnitude 7 earthquake may initially appear as magnitude 5, then grow as more fault ruptures. If warnings are based on early magnitude estimates, they may understate the threat. Conversely, waiting for better magnitude estimates delays warnings. System developers must balance speed and accuracy. Getting warnings to everyone is challenging. Dedicated receivers are expensive and may not reach the poorest residents. Mobile phone-based warnings work only for those with smartphones and may miss people in areas with poor reception. Sirens can alert people outdoors but not those inside buildings with closed windows. Diverse warning methods are needed to ensure equity. The 2011 Tohoku earthquake warnings in Japan were broadcast on television, radio, emergency sirens, and phones, reaching most people. False alarms. When warnings are issued but strong shaking doesn't arrive, erode public trust. If people experience multiple false alarms, they may ignore future warnings. Yet system designers must accept some false alarms, because being too conservative means missing real events. Communicating uncertainty in warnings is difficult, but necessary. Public education should explain that warnings are probabilistic and that responding to false alarms is better than ignoring a real warning. Managing public expectations while maintaining credibility is an ongoing challenge for warning systems. Post-earthquake building inspections identify unsafe structures. After earthquakes, building safety inspectors conduct rapid assessments to determine which structures are safe to occupy and which pose hazards. This critical work must be completed quickly, as people want to return to homes and businesses, but it must also be accurate, as entering unsafe buildings risks lives. Inspectors use standardized forms and training to evaluate visible damage and post color-coded placards indicating safety status. Green placards indicate buildings that appear safe to occupy, though minor damage may be present. Yellow placards mean restricted entry, typically because of significant damage requiring careful evaluation or limited access for retrieving belongings. Red placards mean unsafe, do not enter, used for buildings at risk of collapse or with other severe hazards. The placard system provides immediate visual information to residents, emergency responders, and officials about building safety throughout affected areas. Large earthquakes can damage thousands of buildings, overwhelming local inspection capacity. Mutual aid agreements bring inspectors from unaffected areas to help. Volunteer engineers and architects with training in post-earthquake assessment supplement official inspectors. Despite these efforts, inspections can take days or weeks to complete, leaving residents uncertain about their home's safety. Some people ignore placards and enter buildings anyway, risking injury from aftershock-triggered collapses. Decisions about damaged buildings have profound consequences. Repairing buildings is expensive, and some owners may lack insurance or resources. If officials condemn too many buildings, the economic impact is worse, and displaced residents face housing shortages. If they're too lenient, people may occupy unsafe buildings. Balancing safety, economic, and social considerations is difficult, especially under time pressure. Post-earthquake building inspection systems continue evolving to provide faster, more accurate assessments, while ensuring that decisions appropriately protect public safety. Temporary housing addresses immediate needs after earthquakes. When earthquakes damage or destroy homes, providing temporary shelter becomes urgent. In cold climates or during rainy seasons, exposure to elements threatens survivors' health. Temporary housing serves as a bridge between immediate emergency shelter and permanent reconstruction, which may take months or years. Different approaches include emergency shelters, temporary housing units, rental assistance, and host families, each with advantages and challenges. Emergency shelters in schools, community centers, or tent camps provide immediate refuge, but are only suitable for short periods. Lack of privacy, sanitation challenges, and disruption to normal life make extended stays difficult. Temporary housing units, like trailers or prefabricated cottages, offer more privacy and amenities, but take time to deploy and require suitable land. After the Kobe earthquake, Japan built thousands of temporary housing units in parks and open spaces, where some residents lived for years. Rental assistance programs give displaced residents money to find housing in the private market. This approach works where rental housing is available and undamaged, avoiding need for temporary housing construction. However, it can stress housing markets and disadvantage residents competing for limited rentals. In Haiti, rental assistance worked in some areas, but was ineffective where no suitable housing existed. Staying with host families, friends, or relatives is another option, though it places burdens on hosts and may not be possible for all displaced residents. The challenge is avoiding temporary housing becoming permanent. After many disasters, temporary units meant for months or a year, house residents for much longer because reconstruction is slow. These settlements can develop into permanent informal neighborhoods with inadequate infrastructure. Efficient temporary housing strategies include realistic timelines, adequate support for residents, and acceleration of permanent reconstruction, so temporary phases genuinely remain temporary. The goal is providing dignified, safe interim housing while working toward long-term solutions. Economic impacts of earthquakes extend far beyond physical damage. Earthquake impacts include direct costs of destroyed buildings and infrastructure, but economic effects ripple much further. Businesses close, workers lose income, supply chains break, and economic activity declines. These indirect and induced economic impacts can exceed direct damage costs, especially when critical infrastructure like ports or power plants is affected, or when key industries are concentrated in damaged areas. The 1995 Kobe earthquake caused an estimated $100 billion in damage, but economic impacts exceeded that figure. Kobe was Japan's second largest port, and its closure disrupted international trade, Manufacturing plants couldn't operate without power and water. Companies relocated operations to other cities, and some never returned. The earthquake struck during Japan's economic stagnation, and some economists argue it delayed recovery. Regional GDP declined, and the city's economic position relative to other Japanese cities permanently changed. Supply chain disruptions from earthquakes can have global impacts. The 2011 Tohoku earthquake and tsunami damaged factories, producing automotive parts and electronic components. Factories worldwide had to slow or stop production due to parts shortages. The interconnected nature of modern manufacturing means earthquakes in one region can affect economies globally. This vulnerability has prompted companies to diversify suppliers and hold larger inventories, though these measures increase costs. For individuals and households, earthquake impacts include lost income when workplaces are damaged, costs of temporary housing, and depletion of savings to cover uninsured losses. Even those whose homes survived may face economic hardship if their workplace closed or the local economy contracted. Full economic recovery typically takes much longer than physical reconstruction. Understanding these broader economic impacts helps governments and organizations plan more comprehensive recovery support that addresses not just rebuilding structures, but also restoring livelihoods and economic vitality. Earthquake prediction remains the holy grail of seismology. Despite decades of effort, earthquake prediction, meaning specifying the time, location, and magnitude of a future earthquake with enough precision to justify evacuation, remains impossible. Many claimed precursory signals have been investigated: changes in groundwater levels, radon emissions, electromagnetic anomalies, animal behavior, and more. Some show promise in laboratory settings or appear before some earthquakes. None has proven reliable enough for operational prediction. The fundamental challenge is that earthquake nucleation involves complex processes at scales we cannot observe directly. What happens at the moment a locked fault begins to slip, transitioning from stick to slip? How large must the initial rupture be before it becomes unstoppable and grows into a major earthquake? These questions remain incompletely answered. Without understanding nucleation, predicting when it will occur is like trying to predict exactly when a stretched rubber band will break while unable to examine the rubber itself. China has invested heavily in prediction research and claimed some successes, most notably the 1975 Haicheng earthquake. However, this success was followed by failure to predict the 1976 Tangshan earthquake, which killed hundreds of thousands. The Haicheng success may have involved luck as much as science, with a long foreshock sequence providing clear warning. Most earthquakes don't give such obvious precursors, making the Haicheng case more an exception than a model for prediction. Some seismologists argue that earthquake prediction may be fundamentally impossible because earthquakes are chaotic processes where tiny differences in initial conditions produce vastly different outcomes. Others remain hopeful that better instrumentation, particularly near faults at depth, might reveal precursors. The consensus is that short-term prediction will not be achieved soon, if ever. Instead, efforts focus on long-term probabilistic forecasting, early warning, and improving societal resilience to make prediction unnecessary. If communities can survive major earthquakes without catastrophic losses, whether we can predict them becomes less critical. Probabilistic seismic hazard assessment guides building codes. Since earthquakes cannot be predicted, seismologists use probabilistic seismic hazard assessment to estimate the likelihood of different levels of ground shaking over specified time periods. These assessments combine information about faults, historical seismicity, ground motion models, and site-specific geology. to calculate the probability that shaking will exceed certain thresholds. The results guide building codes, insurance rates, and land use planning. A typical hazard assessment might calculate that a specific location has a 10% probability of experiencing ground shaking exceeding a certain intensity in the next 50 years. Building codes then require that structures be designed to resist this level of shaking without collapse. Different structure types may be designed for different probabilities, with critical facilities like hospitals required to survive rarer, more intense shaking than ordinary buildings. These assessments involve significant uncertainties. Fault slip rates may be poorly known, particularly for faults that haven't ruptured in recorded history. Ground motion models predict shaking based on magnitude, distance, and site conditions, but actual shaking in any specific earthquake will vary. Different expert judgments about these uncertainties can lead to substantially different hazard estimates, which is why assessments are regularly updated as knowledge improves. National seismic hazard maps, like those produced by the U.S. Geological Survey, synthesize probabilistic assessments into maps showing expected ground shaking levels with specified probabilities. These maps form the basis for building codes adopted nationwide or regionally. Similar maps exist for most earthquake-prone countries. The maps ensure that construction standards reflect seismic hazards with stricter requirements in high-hazard areas. While not perfect, probabilistic assessment represents the best available approach to quantifying earthquake risk when precise prediction is impossible. Global seismicity follows recognizable patterns. Looking at global earthquake distribution reveals clear patterns. Most earthquakes concentrate along plate boundaries, with the Ring of Fire around the Pacific Ocean being the most active zone. The belt from Indonesia through the Himalayas to the Mediterranean is also highly seismic. Mid-ocean ridges generate continuous small earthquakes as new crust forms. Transform faults like the San Andreas produce earthquakes along linear traces, but earthquakes also occur far from plate boundaries. The New Madrid zone in the central United States, intraplate earthquakes in Australia, and seismicity in stable continental interiors remind us that no region is completely safe. These intraplate earthquakes are less frequent than plate boundary events, but can still be significant. Their causes are less well understood, possibly involving reactivation of ancient faults under stress transmitted through plates from distant boundaries. The size distribution of earthquakes follows a power law called the Gutenberg-Richter relation. For every magnitude 6 earthquake, there are about 10 magnitude 5s, 100 magnitude 4s, and so on. This relationship holds remarkably well globally and for most regional catalogues. It means small earthquakes are much more common than large ones, but large ones, though rare, release most of the total seismic energy. A single magnitude 8 earthquake releases as much energy as about 30 magnitude 7 earthquakes, or 1,000 magnitude 6s. Temporal patterns are less clear. While individual faults may show rough periodicity in major earthquakes, global seismicity appears relatively constant over time. Each year brings about 1 magnitude 8 or larger earthquake, roughly 15 magnitude 7s, about 130 magnitude 6s, and 1,300 magnitude 5s on average. These averages mask year-to-year variability. Some years are more active, others quieter, but over decades, the rates are steady. This consistency allows planning based on expected seismicity levels, even though predicting individual events remains impossible. Deep earthquakes reveal processes in the mantle. While most earthquakes occur in the shallow crust, some happen at astonishing depths, hundreds of kilometers below the surface. These deep focus earthquakes occur only at subduction zones, in the cold, descending slabs of oceanic lithosphere. Their existence was initially puzzling, because rock at those depths and pressures should deform plastically, flowing rather than fracturing. Yet earthquakes occur down to about 700 kilometers depth. The mechanism for deep earthquakes differs from shallow ones. Instead of friction on pre-existing faults, deep earthquakes likely result from phase transformations in minerals. Under the extreme pressures in the mantle, minerals suddenly change crystal structure, and this transformation can release energy seismically. Another mechanism involves dehydration of minerals in the descending slab, where water bound in crystal structures is suddenly released, weakening the rock and allowing sudden failure. Deep earthquakes provide information about subduction processes invisible any other way. By tracking deep earthquake locations, scientists map the shape and extent of descending slabs deep in the mantle. Some slabs penetrate into the lower mantle below 670 kilometers, while others seem to stall at that boundary. Understanding these patterns helps reveal how the entire mantle convects and how plate tectonics connects to deeper Earth processes. Deep earthquakes are generally less damaging than shallow ones of similar magnitude because the energy has farther to travel and disperses over a larger area. A magnitude 7 earthquake at 600 kilometers depth might be felt over a huge region but cause little damage. However, if such earthquakes occur beneath populated areas, they can still be significant. The 2013 Sea of Okhotsk earthquake, magnitude 8.3 at 609 kilometers depth, was the largest deep earthquake ever recorded and was felt across much of Asia. Earthquakes are part of the planet's natural processes. It's easy to view earthquakes as destructive forces, and certainly they can devastate communities and claim lives. But from a planetary perspective, earthquakes are simply one expression of Earth's internal heat and the tectonic processes that make our world dynamic. Without plate tectonics and the earthquakes that accompany it, Earth would be a very different, likely less hospitable, planet. Plate tectonics recycles the Earth's crust, returning surface material to the mantle at subduction zones and creating new crust at mid-ocean ridges. This cycling maintains ocean basins and continents, concentrates mineral resources, and regulates the planet's climate over geological time by controlling carbon dioxide levels through volcanic outgassing and weathering of rocks. Earthquakes are simply the mechanical manifestation of this grand recycling system. The mountain ranges built by plate collisions create diverse habitats, affect atmospheric circulation and climate, and shape the distribution of life. Volcanic arcs above subduction zones create fertile soils and concentrate rare elements. The deep ocean trenches at subduction zones host unique ecosystems. All these features result from tectonic processes, and earthquakes are integral to those processes. We cannot have the benefits without the hazards. This perspective doesn't diminish the very real human suffering earthquakes cause, but it provides context. Earthquakes are not aberrations or punishments, but natural processes that have shaped the planet for billions of years. The challenge for humanity is learning to live with this dynamic planet, accepting that the ground will shake, and building societies resilient enough to survive and recover. We cannot stop earthquakes, but we can dramatically reduce their impacts through knowledge, preparation, and wise decisions about how we build and where we live. Our understanding of earthquakes continues to grow. Seismology is a relatively young science. While humans have experienced earthquakes throughout history, scientific understanding began only in the late 19th century with the development of seismometers. Many fundamental discoveries are less than a century old. Plate tectonics, the framework for understanding earthquakes, was accepted only in the 1960s. Scientists continue making important discoveries about earthquake processes. fault behavior, and seismic hazards. New instruments and techniques constantly emerge. Dense seismic networks and advanced data processing allow detection and analysis of earthquakes too small to feel, but important for understanding fault mechanics. Geodetic networks using GPS and InSAR monitor ground deformation with millimeter precision. Deep boreholes carry instruments close to active faults. Machine learning algorithms analyze vast datasets to find patterns humans might miss. Each advance brings new insights into how earthquakes work. Supercomputers enable detailed simulations of earthquake rupture and ground shaking. These simulations help test hypotheses about fault behavior and predict ground motion for future scenario earthquakes. Laboratory experiments subject rock samples to earthquake-like stresses, revealing the microscale processes that control macroscopic fault behavior. Combining observations, experiments, and theory is gradually building a comprehensive understanding of earthquake physics. Despite progress, many questions remain unanswered. Why do some earthquakes grow into great events, while others stay small? What controls the size of the largest possible earthquake on a given fault? How do faults interact to trigger or inhibit each other? Can we identify reliable precursors to large earthquakes? As instrumentation improves and datasets grow, answers to these questions may emerge. Each generation of seismologists contributes to building knowledge that helps societies better prepare for and respond to earthquake hazards. We can build earthquake-resilient societies. The ultimate goal of earthquake science is not just understanding, but reducing earthquake risk. This requires translating scientific knowledge into practical measures, building codes that ensure structures survive shaking, land use planning that avoids the most hazardous areas, early warning systems that provide precious seconds of warning, and public education that prepares people to respond effectively. Together, these measures can make earthquakes manageable rather than catastrophic. Success stories demonstrate what's possible. Japan has repeatedly shown that large earthquakes don't have to produce massive casualties. The 2011 Tohoku earthquake, magnitude 9.1, killed about 18,000 people, the vast majority from the tsunami, rather than building collapse. Given the earthquake's size, this represents a remarkable achievement of earthquake-resistant construction and preparedness. Modern buildings largely survived, even in intense shaking, protecting their occupants. California has similarly invested heavily in earthquake preparedness. Strict building codes, retrofitting programs for vulnerable structures, early warning systems, and public education campaigns have made the state much more resilient than it was decades ago. When the next major earthquake strikes, losses will still be significant, but they will be far less than if no preparation had occurred. Each measure, from seismic retrofits to schoolchildren practicing drop cover hold on, contributes to resilience. The challenge is extending these successes globally. Many earthquake-prone regions lack resources for expensive mitigation measures, but earthquake resilience doesn't require expensive solutions for every building. Simple measures, properly implemented, can dramatically reduce casualties. Replacing heavy roofs with lighter materials prevents many deaths in unreinforced masonry buildings. Educating people to evacuate multi-story buildings immediately after shaking stops can prevent deaths from aftershock collapses. Even limited improvements in building construction, if applied widely, save lives. The path to earthquake resilience is not a single solution, but countless small steps, taken consistently over time, building safety into the fabric of society. The ground beneath our feet tells ancient stories. Each earthquake adds a chapter to the Earth's story, reshaping landscapes, building mountains, creating basins, and leaving traces that geologists can read like pages in a book. Offset streams reveal fault motion accumulated over thousands of years. Raised marine terraces record tectonic uplift. Folded rock layers expose the power of continental collisions. The ground beneath us is a vast archive of tectonic history. In the Basin and Range province of the western United States, alternating mountain ranges and valleys record millions of years of extension, with normal faults dropping valley floors and raising ranges. In the Himalayas, spectacularly folded and faulted rocks expose the ongoing collision between India and Asia, which has lasted 50 million years. Along the San Andreas Fault, geologists have matched distinctive rock units, now separated by hundreds of kilometers, reconstructed ancient rivers offset by cumulative fault motion, and traced the fault's history back millions of years. These stories extend beyond human timescales into deep geological time. The Appalachian Mountains, now worn and gentle, record a continental collision that occurred hundreds of millions of years ago, long before the Atlantic Ocean existed. The rocks reveal ancient earthquakes that shook a world unrecognizable to us, when continents were arranged differently and life had not yet emerged onto land. The earthquakes we experience today are simply the latest events in a process that began with Earth's formation and will continue as long as the planet's interior remains hot. Understanding this deep time perspective puts human concerns in context. The earthquake hazards we face are temporary on geological timescales. The faults that threaten us will one day be inactive, their energy spent, their motion accommodated. New faults will form elsewhere. Mountains will rise and erode away. Continents will drift to new positions. The Earth's surface is never static, but constantly transforms. We live in a moment within this vast story, brief but precious. The ground that sometimes shakes beneath us is the same ground that has supported life for billions of years through countless earthquakes and will continue long after we're gone, finding peace with a dynamic planet. As we reach the end of our journey through earthquake science, a larger truth emerges. The Earth is alive with motion and change, and earthquakes are part of that fundamental nature. Fighting against this reality is futile. Instead, we must find ways to live in harmony with our dynamic planet, respecting its power while protecting ourselves through knowledge and preparation. Indigenous peoples and traditional societies have long understood this balance. They lived with earthquake hazards for generations, developing practices and structures appropriate to their environments. Modern technology provides new tools, but the fundamental wisdom remains. Know the hazards, prepare for them, build appropriately, and accept that sometimes the Earth will shake. This acceptance is not resignation, but a mature understanding that humans are part of nature, not separate from it or in control of it. There is beauty in the Earth's dynamism. The same tectonic forces that generate destructive earthquakes also create magnificent mountains, diverse ecosystems, and the mineral wealth that supports civilization. The volcanic activity associated with plate boundaries produces fertile soils, geothermal energy, and spectacular landscapes. We cannot have one without the other. The challenge is minimizing the harm while appreciating the wonder. When the ground shakes, it reminds us of our place in the universe. We live on the thin, cool skin of a planet with a hot interior, riding plates that drift across a molten layer, temporarily inhabiting structures we hope will protect us. It's a humbling perspective, but also empowering. By understanding earthquake processes, we gain some measure of control, not over the earthquakes themselves, which will always occur, but over their impacts on our lives and communities. Knowledge transforms fear into preparedness, vulnerability into resilience. Rest now. prepared and aware. As you lie here, feeling the solid ground beneath you, remember that it's not quite as solid as it seems. It's floating, drifting, accumulating stress that will someday be released. But this knowledge need not cause anxiety. Instead, let it bring appreciation for the incredible planet we inhabit, a world alive with processes that have sustained life for eons. The earthquakes that will inevitably come are part of Earth's story. We are learning to read that story, to understand the patterns, to build societies that can withstand the shaking and recover. Each year brings new knowledge, better tools, more prepared communities. The challenge is great, but human ingenuity and cooperation can meet it. Tonight, as you drift toward sleep, imagine the Earth breathing beneath you. The slow drift of plates, measured in centimeters per year, but adding up to continents moving across the globe. The steady accumulation of stress on locked faults, storing energy for future release. The constant small earthquakes, most too small to feel, relieving tiny amounts of stress. The global network of seismometers, listening, recording every tremor, adding to our collective understanding. Feel the stability of the ground supporting you. Know that scientists around the world monitor it constantly, ready to issue warnings if needed. Engineers have designed buildings to sway and flex rather than crack. Emergency managers have prepared plans and supplies. Communities have practiced their response. All of this protective work happens invisibly, a web of preparation supporting you even as you rest. Let any anxiety about earthquakes dissolve. You have learned about them tonight. You understand their causes, their effects, and the measures that protect against them. This knowledge itself is a shield. When an earthquake eventually occurs, whether large or small, near or far, you will know what's happening. You will remember to drop, cover, and hold on. You will wait for the shaking to pass and then respond appropriately. For now, there is nothing to do but rest. The Earth will continue its slow tectonic dance. Plates will drift, stress will accumulate, and someday it will release. But not tonight. Tonight is for rest, for allowing your mind to settle like sediments in still water. Let the scientific understanding we've explored tonight form a foundation of calm awareness. Picture yourself floating on the surface of the Earth, gently carried by the plates beneath. They move so slowly that nothing seems to change, yet over vast spans of time, they've created everything we see. Mountains and valleys, ocean basins and continents, all from their patient motion. You are part of this grand system, a brief consciousness riding the planet's surface, aware and appreciative of the forces that shape our world. As your breathing slows and deepens, imagine your connection to the Earth growing stronger. Feel supported by billions of years of geological processes. The atoms in your body were forged in stars and distributed by supernovae, gathered into a planet that has remained geologically active for 4.5 billion years. You are, literally, made of stardust, living on a dynamic planet, connected to cosmic processes that dwarf human concerns. The earthquakes we've discussed tonight are simply vibrations, energy moving through rock, waves propagating through the planet's layers. They come and go. Buildings may fall, but humans endure. Communities recover. Life continues. And with each earthquake, we learn more, prepare better, build stronger. Progress is slow, but real. Let all these thoughts fade now. You've learned what you need to know. The Earth is both solid and fluid, stable and dynamic, dangerous and beautiful. We live with these contradictions, finding security not in changelessness, but in resilience, adaptation, and community. You are safe here, now, in this moment. The ground holds you. Sleep comes naturally. Close your eyes and feel the darkness behind your eyelids. Let it spread outward, filling your awareness. Your body is heavy, sinking into rest. Your mind is quiet, thoughts drifting away like leaves on a slow stream. The earth turns beneath you, carrying you through space, a cosmic journey you share with all living things. Breathe in slowly, deeply. Hold for a moment. Release. Again. Each breath connects you to the atmosphere, which connects to the oceans, which connects to the crust, which connects to the mantle, all nested layers of our planetary home. You are one with this system, part of its endless cycles of creation and destruction, growth and decay, motion and rest. As sleep approaches, your awareness of the external world fades. The room around you becomes indistinct. Sound recedes. Even the feeling of the ground beneath you becomes abstract, less physical sensation than concept. You float in a space of deep rest, where earthquakes and all other earthly concerns cannot reach. The journey we've taken tonight, from the basic mechanics of plate tectonics to the human dimensions of earthquake preparedness, has mapped a territory you can now navigate. You understand. And understanding brings peace. Not the false peace of ignorance, which leaves one vulnerable and afraid, but the earned peace of knowledge, which allows informed acceptance. The earth shakes. It always has. It always will. This is not a flaw, but a feature, evidence of a living planet with an active interior. We are privileged to live here, on this rare world, where internal heat drives processes that create continents, oceans, atmosphere, and the conditions for life. The occasional shaking is a small price to pay for all that Earth provides. Rest now in this knowledge. Let it comfort you. The same forces that sometimes shake the ground also create the beautiful diversity of our world's landscapes and ecosystems. Accept this package deal. Dynamic planet, occasional earthquakes, incredible beauty and abundance. It's the only option, and it's enough. Your eyelids are heavy, impossibly heavy. Letting them close feels like the most natural thing in the world. Darkness and peace surround you. The concerns of the day fade. Earthquake science, tectonic theory, all the facts and figures dissolve into general awareness. You understand, and that's sufficient. Sleep comes now, gently, inevitably, like night following day, like tides following the moon, like continents drifting across the globe. Natural processes beyond your control, beyond anyone's control, unfolding as they always have and always will. You surrender to these processes, trusting in their ancient patterns. Good night. Rest well. The earth holds you. Science protects you. Community surrounds you. Sleep deeply now, carried safely through the night on this beautiful, dynamic, ever-changing planet we call home. Sweet dreams.